Hello, can everyone hear? Cool. All right, thanks all for coming again. So firstly, we would just like to wish to acknowledge the traditional custodians of the land on which we are meeting, the Whadjuk people of the Noongar Nation, and we wish to acknowledge and respect their continuing culture and the contributions that they make to the life of this city and this region. So once again, thank you all for coming. I'm Jordan, the current president of the Curtin Students Physics Association for this year. And this is our first real big academic event, so we appreciate the support and all of you coming here to listen to our wonderful presenters today. And thanks for our presenters again for volunteering their time to come and speak to all of us. So I think we have a fair mix here of few high school students, some first years, second years, even some PhD students here and there. So for the first years and second years, this is kind of an opportunity to get a little bit more insight into the various streams which we offer here, because you need to take projects in your later years, in your third years and honors years. So we just hope that this can give you a little bit more help in choosing a stream and choosing something which perhaps might interest you. So I won't take up too much more of your time, but thanks all for coming again, and I'll hand over to Keelan to introduce the first few speakers.
So I think everyone who signed up knows this is the Materials and Applied section of the showcase. So our first speaker is Associate Professor Mark Paskevicius, speaking on hydrogen storage and energy storage in general, I believe.
Thanks, Kellen. It's good to be here. See if I can get some words in before my timer starts. Hi everyone. I'm an associate professor here and in the physics department, and our main research area is energy storage, and it's quite diverse. We look at a few different things in the realm of energy storage, and we're in the physics department, so we focus on some physics aspects of things, but we also overlap with some chemistry and some engineering, which you'll see. So the group's getting quite big now. We have about 30 people in the group, and that's 8 staff members and also 10 PhD and master's students. And there's also quite a lot of undergraduate project students that we have through this year so far. Now, they're not all physicists. We also take in engineers because some of our projects require that expertise. So as you can see, we live in this material science area here in between these 3 disciplines. And really we do need skill sets from all of these things in order to end up with a meaningful product or a meaningful contribution to the field. So what we want to do is take green energy, like renewable energy, from solar or wind or other sources, and store that energy. And the way that we can store it is in a number of different ways, which we'll cover in a second. So energy storage in general, the whole field is covered by this one graph on the top left. So what we want to do is be able to supply energy to meet our demands. And our demands are this red line that may vary over the course of a day. The problem is that renewable energy sources are sort of sporadic, and we can't instantly produce energy to match this demand curve all the time. The renewable energy might be shown in the green area here, but what we want to do is also move some of this energy here, which is in excess, and bring it over here to when we demand it. And in order to do that, we need to store energy. So there's a lot of different ways we can store energy. We look at a few of these. There's a graph down the bottom left that shows a lot of different energy storage technologies, and the y-axis is a volumetric energy density, and the x-axis is the gravimetric energy density. So things like hydrogen, shown in the bottom right, have very high gravimetric energy density. That's the amount of energy that they store per unit mass. But their volumetric energy density is quite low. And this means that we can't store much energy, say, in a gas bottle of hydrogen. Instead, we might want to look at something that we call hydrides. These are chemical compounds that contain hydrogen, which have about the same gravimetric energy density, but much higher volumetric energy density. This way we can store a lot of energy, say, in a car, using these materials. There's another plot that's quite similar here at the bottom, where we can see the current generation of batteries at some particular energy density. And what we want to do is store energy more densely, so our phone battery lasts longer, and our batteries are not so big, and so on. And hopefully even they're cheaper. So what we want to do is look at these new types of battery technologies in order to increase the properties of our technologies. Another thing that's of quite a lot of interest lately is the energy dependency of the world. And you can see here that we have these green and red circles in different parts of the world, which sort of depict the amount of energy that we require as a function of how much we can generate. So Australia has a big green circle because we can generate a lot of energy and we don't need it all. There's other areas like Japan and South Korea that require a lot of energy and they're not even able to generate as much as they need. So what would be a good idea is for us to export energy from Australia to Southeast Asia. And that's one thing that we're doing and looking into, different ways to be able to export the energy. So, as I've said, we split into these 4 different research projects at the moment. These are a few of our main research projects. And one thing we do is try and store hydrogen inside these chemical materials to try and get dense storage for cars, or say a big storage tank for a petrol station. We also want to export hydrogen in different ways, and we're also looking at 2 different types of batteries. We're looking at these solid state batteries shown here. So this is just like a normal phone battery, lithium ion battery, where at the moment the way that lithium is transported between anode and cathode is through this liquid electrolyte. And there's problems with that mean that we're stuck at a certain energy density for our batteries. And in order to get cheaper next generation batteries, we want to eliminate the liquid and replace it with a solid. Another type of battery is shown on the bottom left, which is quite a unique type of battery where we actually operate this battery at about 900 degrees C. It's obviously not for in your phone, it's for putting out at a large scale storage facility. And the way it works is looking at a chemical reaction that has a certain enthalpy and reversing that reaction to get the energy in or out of the material. So this is just a few of the skills that we utilise on a daily basis within the group. Of course, there's this crossover between engineering, chemistry and physics. And one thing we do is a lot of hands-on experimental research. So we're making materials day to day, we're analysing them, characterising them with different bits of equipment that we have around. One thing we do is handle a lot of our materials in these argon glove boxes. So this is where we put our hands in through the gloves, and inside that box is pure argon. There's no air, because sometimes our materials can do things like this and just catch fire as soon as they touch air. And yeah, you don't really want that too often. So we have these physical characterisation laboratories, but we also do some chemistry to make things, because if you want to work with materials, at some point you need to make things. We also work with a lot of international companies who are trying to take this technology to the next level and actually develop products. So one thing I wanted to do is, I've got 2 little case studies here where I'll just focus in on different areas of our research to just showcase certain things about what we do. This is the study with solid state ion conductors, where we're trying to move away from these liquid electrolytes and move into solids. And the purpose of an electrolyte in the battery is to move ions, and in the case of lithium ion, these would be lithiums, but it's very hard to move lithium ions through a solid material. This is a very difficult challenge, and that's where a lot of the research comes in, to try and develop new materials that are able to do this. There's a few existing materials that are well known, different salts in fact, And at different temperatures, they have different ion conductivities. And we want a high ion conductivity for our batteries. These are materials that conduct silver, lead, and sodium, but it's a good example. So at some temperature, these materials have this very large step change in their ion conductivity. And it's actually to do with their crystal structure. At these temperatures, they have quite a change in their crystal structure, which then allows ions to move very rapidly through the crystal. And we want to understand this further. So we look at a class of materials called metal boranes, and they have these big anions in their crystal of boron-hydrogen compounds. And then they have little cations of lithium as well. So when we're designing these materials, we want to design new things that have quite a large anion and also something that has quite short lithium-lithium distances, so our lithium can jump through the crystal and make it to the other end to go from the anode to the cathode. Sometimes we also want partially occupied crystal sites in our crystal. And there's this really unique feature with some of our materials where the anion in our crystal actually rotates extremely rapidly, and that can actually help push the cation along. So this is an example of that. These are these metal boranes. So we have in purple some metals in these crystals, and these big aqua type or teal coloured things are boron cages, which are the anions. And at some critical temperature, our anions become highly mobile and rotate around. And they rotate exceptionally fast, about 10 to the power of 12 times every second. So they're really moving fast. And depending on the shape and type of the anion, it has a different sort of electrostatic charge associated with it, as shown here in our modelling. And that affects the way that it interacts with the cations in the crystal. And in fact, it also affects the way that the anion spins or rotates. So here, this is quite a isotropic anion that's the same in all directions, and that spins pretty much randomly. It doesn't quite spin like this graphic. That's just limited by my PowerPoint skills. But this carborane here has a carbon atom and the rest are borons, and this will spin along its vertical axis here, sort of shown down the bottom here. And changing the way that these things spin and rotate also changes the temperatures when they become dynamic like this, and we can get very high ion conductivities close to room temperature. So the goal is to have high ionic conductivity at room temperature, of course. We don't want to heat up our batteries just to make them work, but we're sort of developing all of these things by working on new materials. Cool. So this is the second case study. For some reason it's got sound, but yeah, pretty much I think the sound is so that the animation works, which is weird. But yeah, what we have here is, this is the high temperature battery that relies on chemical reaction. And what we want to do is store renewable energy. And we can put renewable energy in using electricity, and that can generate heat. And that heat can be used to decompose calcium carbonate and generate carbon dioxide. And this is the energy that we're storing per mole of reactants. And when that CO2 goes back into our calcium oxide again, it generates a lot of heat. And what we can do is turn that heat into electricity using a special heat engine, in this case a Stirling engine. Can't click through that one. Yep, perfect. All right, so Stirling engine is pretty interesting. When we want to turn electricity to heat, that's very easy. We can do that at 100% efficiency. But when we want to go from heat to electricity, it's difficult, and the efficiency is quite low in that conversion. So a Stirling engine works by having a hot end and a cold end, and based on the laws of thermodynamics, the efficiency is limited by what we call the Carnot efficiency. This is one of our industry partners, Texel. They've made this Stirling engine that works at about 900 degrees. And the reason why we want to work at such a high temperature is that the efficiency is higher. So you can see here, higher the temperature, higher the efficiency. And it may seem pretty poor to have an efficiency of 40%, but this is very good for a heat engine. Even electrochemical batteries that are in our phones do have limitations to their efficiency. At some points, especially at cold temperatures, the efficiency is very low in our electrochemical batteries. Can't click them. Thanks. So I'm running out of time, but one of the things I wanted to mention is our thermal batteries are based on cheap minerals like calcium carbonate, and the reason we look at these is because they're dirt cheap. These materials are extremely cheap, and that means we can make competitive technologies that compete against lithium-ion batteries, for instance. One of the reasons why these things haven't been built already is because when we do this, store energy and release energy a number of times, our battery degrades greatly. Some of this is because at high temperatures, everything joins together and fuses. And what we've done is develop a catalyst, a cheap catalyst, that's able to achieve 500 cycles with a high capacity retention in our batteries. So just the last slide. One thing I wanted to mention is that we have this, over the next few years, storage is becoming more and more important, and you can see that the rollout is expected to be high. So it's a nice area to be working in. All right, exactly on time. Thanks, everyone.
Now we do still have question time for Mark here. So we don't yet have any questions on the stream, but if anyone on the stream would like to drop any questions in, that's absolutely fine. But does anyone in the audience right now have any questions for Mark? You have Ashley right there. Let's bring a mic down. Hopefully we don't get any feedback. If we do, I am ready to turn it off.
Thanks for that, Mark. The Stirling engine that you mentioned that was made by, was it Texel?
That's right. Yeah, so it's a 30 kilowatt Stirling engine, and that's about the size of a car engine, a bit bigger. So the other way to convert heat to electricity would be to use a steam turbine. So if you want to go up to the megawatt sort of level of power generation, you could use a steam turbine instead. So that way you would avoid using something like a coal-fired power station and get rid of the coal side and just put in heat from the thermal battery, and that would run the boil the steam and run the turbine, generate electricity instead. So it is scalable, but Stirling engines don't get much bigger than what I showed. 30 kilowatts is about as big as they go. Definitely, yeah. So 30 kilowatts is enough to run 10 houses or something. So you could have several in, a residential area.
So do we have, we have another one from the other Ashley.
Do students that work with your research group have an opportunity to work with the industry partners that you mentioned?
Yeah, so our industry partners are, they're involved in grant funding and ongoing grants that we're working on, and the students would work on those projects that are funded and have some interaction with the industry partners if they're working on those projects, for sure.
All right, do we have anything from the stream just yet? Nothing from the stream yet? Do we have any more questions in the audience then? Yes, we have. You had your hand up at the same time as Ashley, so go ahead.
Yeah, okay. It's a non-technical question. Your first slide aimed to show this mismatch between when the energy is produced and when we use it. And then you said when we use it, or something. Do you see any way the world would change a bit as well, where we would move on where the energy
I don't think so. I think humanity is stubborn, and especially we've gotten used to the fact that we can have energy whenever we want, and it's hard to go back. I think, yeah, in an idealised world that would make sense, to use most of our energy during the day when we have solar, let's say, but I don't think it's practical to do that.
So could you just repeat the question that he asked, just for the people on the stream, because they couldn't hear it?
Sure. So yeah, the question was, can we move our demand to be more flexible? And yeah, I don't think that's viable.
So we've had some interesting questions so far. Do we have any more? Maybe from this side of the audience? No. Irene, did you have a question before?
Yeah, I'm not sure if it's fair and if you know the answer, but you had at some point a picture of a battery that you called fire. We heard a few years ago when the batteries on the phone were getting on fire. Was that the same thing? Was it air leaking, the battery leaking and contacting with air? Or?
No, it was different. So of course, a lot of the materials in a battery are very reactive to air, so if you do puncture it, it can catch fire. But also, I think the Samsung phones that were catching fire was due to a short circuit between the anode and the cathode, and that happened because of this liquid electrolyte allowing lithium dendrites to grow across, and we had like an electrical pathway between the anode and the cathode, and a short circuit, and everything got super hot and caught fire. So that's one of the advantages of solid-state batteries. We can stop this short-circuiting because we don't have a liquid where metals can grow through and short-circuit.
That's going to have to be our last question because we've hit the 20-minute mark there. And so, from hydrogen storage, so thank you, Mark, for that presentation. So from hydrogen storage, we now move on to carbon materials, presented by Dr. Irene Suarez Martinez.
So I thought I'd just talk you a little bit about carbon materials. So I have dedicated my life in research to carbon materials. And some people laugh because it's like, what, one element? Come on, your research is very narrow. And it's true, it's just one element, and sometimes I decorate the carbon materials with other elements. I feel exotic that day and try to move to one side of the periodic table or the other and try boron or nitride. But don't be fooled, because carbon materials are actually a lot of materials in one. There you go. It's one element, but it's actually a whole spectrum of materials, okay? We all know that graphite, which is the thing on the pencils, is made of carbon, but also diamond. So carbon can do two opposite sides of the spectrum. A material that is black, that is made out of layers, that is soft, and that's why we use it as a lubricant, as a pencil, that conducts electricity, and that is when every atom is bonded to 3 other atoms. But carbon, the same element, can make the opposite, can be a gem that is transparent, that conducts electricity, that is the hardest material on Earth. So the flexibility of the carbon atoms to bond one to each other in either to one more atom or 2 or 3 or 4 makes it that is an amazing thing to work on. And I don't work on a single material, even though it's one element. And here I show you some of the materials that are made out of carbon. So you have the polar opposites, the graphite and the diamond, but everything in between. When carbon can bond sometimes to 1, to 2, to 3, so you have things like carbon nanotubes when everything is bonded to 3, but now it's a tubular structure. You have carbon fibers that you may have in, if you have a bike or if you play golf. Now it's a very fashionable thing to have carbon fibers on your golf clubs. and amorphous carbon. There is a whole variety of things there. To show you that it's not only me who is excited about carbon, carbon is the only material, only element who has 2 Nobel Prizes dedicated just to it. We have in 1996, the fullerene, the discovery of the fullerene was given to Curl, Harry Kroto, and Richard Smiley for the discovery of this molecule, which completely changed the way we think about carbon. No one could, now seems a bit like, you can put carbons all around a closed gauge molecule, but at the time, it was revolutionary. No one ever thought, and it opened all this new research about nanotechnology. In 2010, then there was the second Nobel Prize, and this time in physics, and that was for the discovery of graphene, which people have been saying, oh, probably, theoretically could exist, maybe not stable, but they actually produce it. And I remember when Novoselov was actually presenting a poster in a conference, and I was a PhD student at the time, and I thought, yeah, okay, you produce graphene, that's amazing. But most of the people in the room didn't actually believe him. And the way he did it, in case you don't know, it was quite fun. They had graphite made out of layers. They got a sticky tape, and they put it on top, and they peel it off. And then they measure what they have in the sticky tape, and they have quite a lot of layers. So they put another sticky tape and did it again, and again, and again. And they call it the after 5 o'clock project. When after 5, everyone was bored, didn't want to do anything else, what do? Get the sticky tape and start peeling. And measure every time, and eventually they got to one single layer. And they won the Nobel Prize. So these were things that have, very all over the world. But I wanted to focus a bit of what is carbon materials in Australia, because Australia has been extremely innovative on the use of carbon materials. The first of all, it was the tetrahedron amorphous carbon, which is a material discovered here in Australia, first characterized and named by David Mackenzie, still alive and working in Sydney, in the early 90s. And he never patented, but TAC, which is also known, tetrahedron amorphous carbon, is now in the hard drives. It's used as a corrosion layer, so you probably have had it in your hand at some point. In the early 2000s, there is another very important discovery, which is the bionic eye, and this is based on diamond. This was by Stephen Prower, and it used the diamond and the optical properties of the nitrogen and vacancy complex to actually make an eye that can be put on people. More recently, we have carbon nexus, and that's, I think the actual really was 34 million, and in total it was like 100 million that the Deakin University gave to work on fibers. And as I said, fibers are very important and are now commercialized, so this was to push again more on the carbon fiber work. And we shouldn't forget that we all know Rio Tinto is have been having diamond mines, but there is also a lot of graphite mines in South Australia, recently opened one. And we, in this country have a lot of coal, which is also carbon. So I lead the carbon group in physics with Nigel Marks, and one of the good things about having two heads on the same group is that we come from different ways of studying carbon. So Nigel, he did his PhD with David Mackenzie, so he comes from the tetrahedron amorphous carbon, so the carbon which has 4 neighbors, so he knows a lot about the diamond and the amorphous structures. And he worked on astro, looking at the radioactive material. Well, I come from the atoms the carbon atoms with 3 neighbors, so what is called the sp2. So I did my thesis on graphite. I have worked in all the carbon nanoforms, so on the tubes, on the fullerenes, on the graphene, and many exotic ones. And what we do in the group, we have 2 we do a lot of theoretical work, a lot of models. So we do atomistic models based, which we use the POSI center, so we use the supercomputers, and we can visualize them. And this is a picture of us in the hive. Inside, you could put the glasses and walk around a nanostructure. We also do synthesis, so we do a lot of work on making the materials and characterizing them. So here you have, in that side of the image, you have the magnetron, which is a sputtering machine you could do coatings, and thus you could make tetrahedrons amorphous carbon there, but you could sputter other things that are not carbon too, and we also do that sometimes. And here on this side, we have an XRD, because on the bottom of the the top of the physics department on the 3rd floor, we have a lot of excellent X-ray diffraction equipment for powders. So our samples are mostly powders, black powders, and we use the XRD to analyze them. I thought I finished telling you a little bit of examples of things that we have done. So as I said, we create atomistic models. One of the things that we do, for example, is that activated carbons, which you may have used to purify your water and put them in filters, we don't know the structure of that. And engineers sometimes are using too simplistic models. So we have created realistic and reliable models for these materials, which means now that engineers can actually study them. Because that wasn't possible before. It was just, putting so many assumptions that at some point you lost track of what you were actually looking at. So this is an example of one of those structures. So we use each corner there will be, each stick is a bond, and then so you have, in some cases, we could have 1 million atoms in a structure, which is quite challenging. But we also look at how things agglomerate. So another project we have had is looking at how, all the carbon in the world comes from the stars. So how the small molecules, organic molecules, get together in the interstellar space, and how they agglomerate and then form bigger clusters of carbon, which eventually they arrive to Earth. So that's kind of a lot of our work on models. We can then squish them, heat them, do anything to the model to work out what happens to the material when they are under these conditions. What we can also do is actually do it. We can heat them up. And one of the things we do in the building is we heat up structures or materials to really high temperatures. And when I mean high, Mark was saying 900, I'm talking 3,000 degrees. 3,000 degrees is half the temperature of the sun. So we have special equipment which we have tweaked to make them heated, because normally conventional ovens are super expensive. There is a handful of them on the world only that get to that temperature. So we have this machine, atomic absorption spectrometer, which basically is used to vaporize things, but carbon doesn't really vaporize. So when you heat it, you can get to 3,000 degrees and some reactions start to happen. And we could get graphite, which is quite interesting because we could use it maybe for batteries. All this work really is to then explore new applications of carbon materials. So we work with engineers, we work with physicists, with people in health to try to then place these things and find new ways of using carbon. One of the examples is in bioimplants. So for example, carbon, is a biological, very biocompatible. The bionic eye is a perfect example of this, but in many other situations. So if we can get a carbon by tuning in this spectrum, find a carbon that matches the properties of bone or teeth, we could use it for bioimplants. So that is because, there's a lot of rate of bioimplants being rejected, implants being rejected. So using maybe this type of this research to put it in bioimplants. Another one is getting these porous materials to use them to store hydrogen, which is a link that we are establishing now with the hydrogen group. So carbon is a spectrum of materials, and it can do a lot of things. We just need to learn how to tweak and how to choose the right material. And that's it. I'm done.
Well, you've given yourself 7 minutes of question time, so we have time for a lot of questions, and I certainly hope there are a lot of questions, because carbon's a very interesting material. So let's start with the audience, of course. So any questions from the audience on carbon materials? We got one up the back from Jordan.
Yeah. So what would your kind of day-to-day research like be a bit more? Because I understand you do a bit with supercomputers and things like that. So what would that look for perhaps students interested in going into academia in this area?
So on a day that I am working on models, so most of the time what I do is called molecular dynamics simulations. So those are basically looking at the process with time, but the time is really short. You model, you normally, picoseconds or something like that. So a lot of it is running the calculations in the POSI center. So you are in your desk, you are on your computer, you just send your calculation to be run on these hundreds of nodes they had on the supercomputer in Tech Park. Getting the results and involves a lot of coding as well. So you need to, people in the group, I mostly run things on Fortran, but people in the group like Python, C++ once upon a time, people liked it. So it's a lot of coding, a lot of visualization as well. So making figures like this, like making the models, and also analyzing them, like making code that count how many pentagons, how many hexagons, or things like that. On the day that I am with IceMore Lab, then it's probably just getting frustrated at the machines when they work. No, the PhD students actually run most of the experiments, and some of it is run here, some of it run is in UWA. But yeah, that's more like lab-based work, preparing samples and putting them in the XRD machine.
We have another question right here.
So there is different supercomputers in Australia. Oh, the POSI. Igor would probably help me on this. Do you know how many nodes have POSI? I never use GPUs, I'm more on a CPU, but there are projects as well on CPUs. We are trying sometimes to rewrite the codes to run on GPUs. But yeah, so there's a lot of, that's one of the good things of being in Western Australia to do this type of projects, is the resources that we have here.
We have another question from Ashley again.
Um, yeah, so I did a undergraduate on chemistry. I think in material science the thing starts to be very blur of who is a physicist, who is a chemist. So I did an undergraduate in chemistry, and then I did my PhD with a physics person. So it's all relative. What we do, it will be some of the physical chemists' interest rather than synthesis as a inorganic or organic chemist. Because what we do is more transformation from solid state to solid state. So in terms of heating or using pressure to do those transformations rather than chemical reactions.
Do we have any questions from the stream just yet? No questions from the stream, so another question from the audience then.
No. But you can't go hotter because, so graphite is refractory. So I'm not sure how you will get much hotter than that. I think it's, the theory says that graphite, or any other carbon actually, carbon will turn into liquid at 4,000. I don't think anyone has got that. But yeah, 3,000 is, I think, to be honest, in particular in this equipment, the 3,000 is not set on a stone. Like it's not, like I wouldn't bet that it's 3,000 or 3,100. Is because this machine, what it's do is a chemist, is used for chemists to analyze compounds, and what they want to do is to vaporize the sample. So they don't really care that much about the temperature. What they do, they have a knob, and then they go, okay, try this temperature. Did it vaporize the sample? No. Okay, turn it higher and go. They never get to 3,000 because 3,000, absolutely everything has vaporized instead of carbon. So the knob on that machine is very unreliable. So we are getting a new one where we will be able to tune and be sure that if it's 3,000, it's actually 3,000 and not 3,005. But I think it's still, the limit is there. I don't think we can get too much higher.
So that'll have to be our last question for Irene. However, Irene will be back for the panel at the end, so if you have any more questions about carbon materials then, you can ask them then. So we've had two interesting presentations about materials science now, but now we're moving on to applied physics. So we have a presentation now on remote sensing and marine optics from Professor David Antoine. Please correct me if I pronounce that incorrectly.
better like this, maybe. Thanks. Yeah, and that's what I'm going to tell you a bit more, is what we call this ocean color radiometry. So that's the specific techniques we use from space. And when you do all this, then you can use these techniques to look at the environment and try to understand what's going on in the oceans, and that's what we sometimes call satellite oceanography, which basically means doing oceanography using observations from space. So just a quick and relatively naive sketch of what this ocean color radiometry is. So you have the sun, sunlight is penetrating the oceans, interacting with everything there. So of course with water, but with all sorts of particles, living particles, non-living particles, these sort of substances. And this is changing the amount of light which is backscattered to space and the spectral composition of this light, whether it's more or less blue, green, or whatever. So when you understand what's going on here, and you measure this with a remote sensor, so then you can infer this, the parameters of interest in the water. And you know, yeah, the water color is changing, definitely. You can have this variety of conditions if you look at this in the open ocean waters, from very blue to relatively green waters, and you will know why. If you go closer to the coast, you have all sorts of influence, and you can all have this variety of colors. And from this, you can infer, you know, what's in the water, basically. So of course, you know, if you have on one side something like this, which is here an image of the microscopic realm of ocean phytoplankton. Phytoplankton means this microscopic algae floating at the surface of the oceans. On the other side, you have a satellite on top of the atmosphere making radiation measurements. And of course, what we want to do is to connect this. So that's where the physics and the maths come into play, because you need to work on, again, this absorption and scattering properties of all these little particles. So then you understand how they scatter and absorb light and transform what the satellite is going to see. So again, radiative transfer, numerical inversion techniques, of course, because then when you have understood what we call the forward problem, is how the satellite, the signal you observe at the satellite level is formed, then you want to inverse that and go back to the properties of interest. And yeah, that's this last point. There are many of satellites we can use to do this now. It all started in the late 1970s, and there are a series, and there are many more than that actually in space now. And the tools and the techniques so then we need to develop and to use are the following. The first thing is there is still a lot of what we call field work to do, because if you want to understand how the particles interact with light, you need to characterize these particles, you need to go at sea, you need to measure all that thing. So there is a lot of field work which is actually underpinning the satellite remote sensing work. So then you need to develop numerical inversion algorithms. So that's again, a variety of techniques, including now these techniques included into the generic name of artificial intelligence. Then you have to process huge amounts of observations, because, you know, these satellites are orbiting around the Earth, collecting data permanently over years and years and years. So that's billions of observations that you need to process at the end. And you need to do a lot of modeling as well to understand the process, understand the signal you measure, and derive some other quantities as well from this. So, and some questions we try to address, for instance, are here. So how the phytoplankton amounts and composition change in the coastal and open oceans, from seasons to interannual scales and to much longer time scale in response to climate change, for instance. And how these little things fix the carbon. Well, still a bit of carbon here. So that's the process of, as you know, of photosynthesis. So they take up carbon dioxide and produce organic matter in the oceans. That's close to 50 billion tons of carbon every year, which are transformed in this way by this tiny phytoplankton. How this is feeding then the higher trophic levels, because the phytoplankton is the basis of the entire food web in the oceans. How do the water quality and habitats are changing in coastal areas? That's a very important topic at the moment. And if you wonder, what's the usefulness of all this, I have listed here a number of the possible users and actual users of the outcome of this research. So the fisheries industries is, of course, very interested by this. Defense, sometimes, all the agencies which have a responsibility to monitor and safeguard the environment, and of course the International Space Agencies who are developing all these nice tools for us. So at the moment in our group we have three main focus areas. So we look at the coastal areas of Western Australia, at the Indian Ocean and the Southern Ocean as well. And this map here is just showing you this concentration of this phytoplankton over the entire globe as we can derive from this satellite. So you can see from very blue desertic type of areas to much greener areas where the phytoplankton concentration is way higher. So a number of things we did recently and still now. I told you at some point that we need to do quite a lot of field work, and that's exactly the illustration I wanted to have here. So we did, for instance, a 3 months circumnavigation around the Antarctic. That was in 2016-17 on this big ship. This is the track of the expedition. So 2 years ago, we did another 1 month in the Indian Ocean like this. And we work as well a bit more locally, so you can recognize here Rottnest. And we have a site here where we deployed this kind of instrument that we use, as I told you before, to understand what's going on in the water. And we use that as well to validate what the satellite is telling us. Because, satellites, when they are in orbit, of course, you have little possibility to go there and to do anything on the instrument. And so you need to check regularly with ground measurements that your satellite is telling you the truth in some way. A few things we are involved in at the moment as well. You may know or you may not know that Australia doesn't have any sovereign satellite capabilities for the moment. 2 years ago, we had a space agency created, so that's one step in this direction. And now there are a number of projects to try to develop Australian-based satellite missions. And among those, there is this one, which is called Aqua Watch, which is about looking at water quality in inland and coastal waters, so the lakes, the rivers, and coastal waters. And that would be, ideally a system like this. Of course, this complete vision is probably something that we might get into maybe 10 years from now. But there is a lot of development, a lot of capacity building to do in the country to get there. But that's the sort of things we are involved at the moment in the preparatory phase. Oops. Other things we do, well, I don't look at the details of these things, just to show you the kind of flow and pathway we do from satellite products to the things we really want to understand about the oceans. And we have a project at the moment which is trying to improve the quality and the consistency of these products when you use different sorts of satellites. I show you a slide with, I think, 6 or different satellite missions that we can use. It's very good to have all these things, but of course, not everyone is going to tell you exactly the same story, so there is a lot of work to improve consistency between these different missions and merge the products into this kind of final maps. And the last one I wanted to show you is kind of an exciting thing we are going to do. Well, still in a few years, there is still a bit of time before we get there. It's an expedition again. It's a 3-year expedition around the Southern Ocean that will start probably 2024. Again, the same logic. Well, there are plenty of things that will be done on this expedition, but among these, we want to collect as much as we can to, again, validate what the satellite products are telling us in the Southern Ocean. That's going to be a big platform like this, floating and drifting around the Southern Ocean for years, with a number of people sitting here and going around the Southern Ocean. Well, so why we want to do this? It's because this part of the world is really, really hard to access. So there are very few measurements, and this platform would allow us to collect way, way more measurement than we did before. And yep, and I think that's it. Thank you.
So now we've got questions for, is it David or David, by the way? You can do both, okay. So I'm going to actually lead in with a question of my own, which is, you're in marine optics, but there are people at Curtin in marine acoustics as well. So how often is there collaboration between those two fields?
There are actually, this expedition I just showed you had a very significant acoustic program attached to it. And when the acoustics and the optics come together, it's not so often, but in our case, it's when we want to, again, understand a bit better the particle distribution in the oceans. With the optics, you can address a certain range of the particle size, basically. And with the acoustics, you would have access and you would characterize to another range, or basically to bigger particles. And by combining both, we can get a better idea of what's going on. Because what we call the particle size distribution is a very important parameter in determining the optical properties, like absorption and scattering.
Well, I'll stop being selfish now and I'll throw to the audience. And we have another question from Ashley.
When students work on the projects, do they have an opportunity to get out and do field work? Oh yes, of course. Yeah, that's similarly to what Irene said. That's a very interdisciplinary field or multidisciplinary field. So you can come to these kind of things from physics. You can come from biology. You can come from engineering as well, because this phase now where we enter into trying to build new stuff from new satellites in Australia, there is a lot of engineering, of course, needed behind this. So there is a variety of profiles and backgrounds that are definitely adapted to what we do. Yeah. So yeah, if you want to get wet, it's time.
So do we have any more questions from the audience right now? And once again, the other Ashley.
I don't know a lot about getting data off satellites, but I assume a lot of the time you get given a large data set that's been collected. Do you ever get to log into a satellite and control it live?
Nope. There are some of these missions were launched with the idea that not everyone, of course, but at least the space agencies could sometimes tune a bit the system, change, for instance, the spectral bands or things like this. It has not been used very much because there is a big activity and a big aspect behind this is the calibration of all these instruments. That's a very critical task, of course, if you want to get something right at the end. And if you start to tweak the instrument and to, try to modify this and that, of course, each time you would have to redo the calibration, which you can do in some way indirectly from the ground, but there are a number of things you just cannot do. You would need the instrument to be in a lab to do this, so, yeah.
So
And sorry, just maybe what I can add to this, is satellite remote sensing is very often seen as a relatively qualitative way of looking at things, making nice images and looking, oh, there's this and this and that. In that case, and that's why we were sitting initially in the physics department. We now sit in the School of Earth and Planetary Sciences, but it's because the interpretation of the signal we do is grounded in physics, so we really want to quantify things. You know, on each of these little pixel of observation and billions of observations, we want to quantify things with units, and then we can use this, you know, to describe the environment, follow the environment, use this into modeling, etc., etc. So that's a quantitative side of remote sensing, I would say.
So we've had quite a few interesting questions from our actual panelists and presenters. So can we try to get some questions potentially from this end of the audience, from our guests, audience? We have one right up the front here.
Oh, okay, yes. Actually, this thing is new in some way, but not new at all in other way. It's new because, okay, it's being built, it's going to be built probably next year, blah, blah, blah. The principle has been actually already developed. It was a ship, because that's a ship. We still can call this a ship. That was designed and built by the US Navy in the 1960s. And it has been used until very recently, actually. It has a very long life. It's basically the same principle, and it was used initially to listen to submarines in the Pacific. So that was what the US Navy was doing at that time, probably still, by the way. The principle is you have this part here, which is a huge ballast. So the thing is brought horizontally on the sea, then the ballast is filled with water, and the entire thing flips to the vertical position. Well, there are a number of engineering characteristics that will make it extremely stable, so there is extremely limited vertical movements, even with big waves, and that's what you need when you go into the Southern Ocean, of course. And then it will drift basically vertical, you know, with small oscillations, of course. And there will be a myriad of measurements from, you know, measuring the incoming light, measuring all that stuff in the ocean I just mentioned before, taking samples of water, doing analysis, measuring the radiometric properties and the acoustic program, which is a very big part of the expedition as well.
So that'll have to be the last question. We're almost at 21 minutes. We've gone a little bit over here. So let's thank David again for that presentation. And our next presenter, I'm not sure if he'd be classified as materials or applied, or in fact both. So on materials, he wants to be materials. So so we have a presentation from Professor Charlie Ironside on semiconductor materials, wasn't it?
So it is on. Hi. And how do I use this? Actually, just so it's just left, right. Oh, there. Hi. So what I'm going to talk about is a particular group of materials, semiconductors, and how they're used in semiconductor technology. And in particular, I'm going to focus on a device called the vertical cavity surface emitting laser. You might have one on your phone, and I'll show you how it's used. So semiconductor technology is foundational to computing and telecoms. Sort of dominates the modern world, really. Most of it's silicon, But we're going to talk about another type of semiconductor called gallium arsenide, which is used to emit light. Silicon doesn't emit light very well, but this material does. And we're going to take as an example the aluminium gallium arsenide VCSEL. And we're going to analyze it using something called focused ion beam, time of flight, secondary ion mass spectrometry, nanoanalysis. We're going to look at these devices and figure out if they're made properly, so that do they work properly. So the VCSEL market has gone crazy in the last few years because it's gone into mobile phones and it's used for facial recognition. So if you've got a phone that recognizes your face, it illuminates your face with light from VCSELs. And that's how that works. So just before I start, I thought I'd just, that's the point. I'm going to talk a lot about nanometers. So let's orientate ourselves and figure out how big is a nanometer. This is a fly. It's a midgie. It's a sort of Scottish version of a mosquito. This is its eye here, and this is what it bites you with. Sticks that in, draws out the blood. And if you look at that, that eye is a compound eye made out of islets, and this is an islet here, which is 10 microns across. That's where semiconductor technology was in the 1970s. Now, see the tip of the hair? That's 100 nanometers. Actually, we're beyond that now. We have silicon devices that have got features on them down to 7 nanometers. When I made that about, 10 years ago, 100 nanometers was it. That was as small as we could make anything. Now we're 7 nanometers. So that gives you an idea of the scale of things. So we're going to talk about the VCSEL, and in particular, how it's used here. This is somebody illuminating their face with VCSEL light. And what it does is illuminate your face with a whole series of dots. And for how those dots get distorted, the phone works out the 3D information present in your face. You can't see these dots when you normally have your phone because you don't see in the near infrared. These dots are a wavelength around about 800 nanometers or so. You can't see that. So what does this device look like? This is an SEM picture of it. That's where the light comes out, that little dot there. And if you look at it in some smaller scale, you'll see that the light is emitted from here. The electricity goes in, the current flows through this contact. And that's 20 microns across. This thing's about 10 microns, but it's got things that are smaller than that in it. Oops. So this is what the structure of the device looks like. We have here, this DBR stands for distributed Bragg reflector. So these are layers and layers of semiconductor material, about 250 nanometers of them, these layers. If the wavelength of the light fits that, it gets highly reflected and bounces backwards and forwards, up and down here, and then is emitted out at the top of the device. So that's how this laser works. What key point that's difficult to make is this thing here called the oxide aperture, which is here. We try and confine the current and that flows down into this device, into this region here, and to do that, we put in this oxide, which doesn't conduct electricity, and it blocks the electricity in this region, but it lets it pass here where there isn't any oxide. So that's what we're trying to figure out with our tools that we've got in the John DeLater Center, if this oxide's been made properly. There's billions of these devices made every day. They all have to operate the same way. It's a difficult task for engineers and physicists to get this right. And if they don't work, they can't be used, and that's a yield problem then. So we're trying to figure out how best to make these oxide layers and if they've been made properly. On to the next one. Oops. So that's an actual SEM picture, so it's scanning electron microscope, doesn't come out too well. But you can sort of see the layers here. Those layers are a few nanometers wide. So how do you make something like that? You use a technique called MBE, molecular beam epitaxy. So these are called epitaxial layers, and those epitaxial layers are made by putting down almost individual atoms. There's only about 500 atoms thick, those layers. It's materials technology to the point where you can actually put atoms on top of atoms. It's something you can't hardly believe, and you can actually get to the ultimate in controlling material composition. So we look at it with a thing called time-of-flight sims, which what happens is we hit the surface of our sample with a primary ion, and that causes a secondary ion to be released from this sample surface. As we do that, we're also sort of etching away the material. We actually weigh the secondary atoms by a technique known as time-of-flight mass spectrometry. So the heavier atoms, we have a pulse comes down it's actually gallium ions, hits the target releases atoms, and those atoms take a certain amount of time to get to our detector. We measure that time, and the heavier atoms take longer. So we can identify the atoms using this technique. And then we're going to look for the gallium, the aluminium, and the oxygen in particular. That's what we're interested in. So we can map out our device and figure out if it's okay or what's gone wrong with it. So that's what we did in the John DeLater Center. We hit it with this beam. The beam actually sort of mills away, or oops, gone the wrong way there. The beam mills away the device. Each pulse releases about 0.5 million ions that we analyze. So we've got a fair amount of ions to look at. And we've sort of got what we call a voxel, which is a bit like a pixel, but it's in 3 dimensions, which is 800 nanometers across and 4 nanometers thick. And we remove that amount of material every time we pulse it. And that gives us a resolution with which we can map out the device. Now we end up with a huge amount of data. We've mapped all the atoms in our device, which is about 2 microns by 2 microns. But we've done it on a nanometer scale, and we've mapped all the species that we're interested in. So it's a lot of data. So what we did was visualize that. Could you run that? Is it? Okay, so this sort of takes you a little bit over what we've just talked about. So this is the nano analysis with Fib Sims, and we actually used the Hive, the visualization facility at Curtin. We're looking at the VCSEL device. We're looking at these gallium arsenide layers and the oxygen layers, and here it is. So the color code is over there, and we're trying to get it visualized so the engineers can use it. Now, what they're particularly interested in is, oops, sorry, can't. Yeah, good. Thanks very much. Yeah. So what we're particularly interested in is the red stuff, which is the oxygen. We want to know, where did the oxygen go in this device? And you can see the layer structure there. That's the aluminium. This is actual real data. It's not a visualized. It's not a computer model. This is data. And that's the oxides. And we want to see the oxides well separated and where they should be, not getting out of position. It's a major cause of failure of these devices, that the oxide actually goes to places you don't want it to go to. And that's the picture that you get of the full device. So that was done at the Hive, and this company made the VCSEL, so that's Compound Semiconductor Technologies, which they're based in Scotland, and it's quite a lot of my old students set this company up. They make these devices for mobile phones. There's other things they're used for. You get them in computer mice or mouses. You get them in LiDAR for cars. You know, the smart cars use a technique of sort of radar type technique, but it uses light, so it's called LiDAR. And they use VCSELs for LiDAR quite a lot of the time. So, moving on. So, semiconductor technology can make entirely new materials with absolute atomic precision. It's had to do that. It's followed a thing called Moore's Law for the last 30, 40 years, where it's doubled the number of transistors on a chip every 2 years. And to do that, things get really, really tiny now. We're down to 7 nanometer gates on silicon transistors. And think about that in terms of the fly. That's the tip of the fly's hair. It's an amazing piece of work. And with the FibTOF SIMS, we can actually construct a 3D visualization of the map of the atomic species in a VCSEL. And we could do that with other semiconductor devices. We could look at the MOSFETs to make up that's metal oxide field effect transistors, which make up most of your microprocessors on your phones, etc. So we can look at these devices with absolute precision, with a resolution of a few nanometers, and that's an amazing tool. And it's currently being used to try and identify failure mechanisms in devices. Okay, well, that's me, thanks. Thank you.
So we'll move on to questions for Charlie on semiconductors. So do we have any questions from the stream? Still none? Okay. So let's go for the audience then. Do we have questions on at the front again? Yep.
Yeah, hi. Okay. So the question was, why do the semiconductor devices have to be so small? Yeah. Well, in your microprocessor, for example, the more transistors you can get on the chip, the more functionality you can have. You can have more memory, you can have more processors, and that means that you get better functionality from the device. So it'll work more quickly, and you'll have more memory, so you can do more stuff. And the reason that these devices are small is because they have to fit on a phone. You couldn't have a large bulk laser illuminating your face. You need to use very compact devices for that. What now actually limits semiconductors more than the dimensions is the heat that is generated. So you generate a lot of heat in a small volume, and the faster you run your chips, the more heat is generated, and so you have to dissipate that heat as fast as you can. You might notice if you make your computer work really hard, you hear the fan switch on. That's because we have to dissipate the heat from the chips. So that's currently the real bottleneck in really fast computing, is how you get rid of the heat.
So say you have a very small computer slapped on the back of a very large screen, say like that one right there, how much cooling would a computer like that need?
Right. To give the numbers are, if you talk to Intel, who make a lot of the chips, they say that in terms of the surface flux of heat, a microprocessor has to dissipate more heat than the surface of the sun. It's an amazing amount of heat that it deals with. It's not so much the total quantity of heat, it's the volume of the heat that it's in. So what's the real enemy is the temperature. If the temperature goes up, and that's because you're putting a small amount of heat, but in a very, very small volume, then if the temperature goes up too much, your semiconductor is no longer really a semiconductor, it turns into something that's more like a metal. And then the device stops operating.
Let's jump back to the audience. Do we have more questions for Charlie? Ashley with another question.
Yeah. Yeah. Yeah, they still send me devices to look at, and their main business now is actually lasers for broadband. So they make a lot of the lasers that are particularly going into the Chinese market for broadband, and they get their stuff packaged in Taiwan. It's quite interesting. We can make like 40,000 lasers on a wafer, but we sell those lasers for about $1 each. The real money that's made in this business in terms of telecoms is in packaging those lasers so that the laser can feed nicely into an optical fiber and be used for a broadband connection. Yeah, so those VCSELs are also actually used quite a lot in data centers where you want to actually communicate between computers in the same data center. You can almost have like what we call free space. That is, we don't use fibers, we just have the things pointing at each other. That's a big thing, sort of server farms. All the computers in a server farm have to talk to each other really quickly.
So do we have any more questions from the audience at the moment? Right up the back there.
Yeah. Well, we get all the resolution we need by the time of flight. If you needed really high resolution, then you might go to a large scale, as you say, it's usually a magnetic field type of technique where you have a magnetic field, a graded magnetic field where they end up in different spots actually. But the time of flight works really well for us. In fact, you might notice that we're looking at gallium, arsenic, and we're using gallium for the FIB. The focused ions that we use are actually gallium. So you think, well, how do you discriminate between the primary ions that you're hitting the thing with and the secondary ions that are scattering? What we actually use is a particular isotope of gallium for the primary beam. And we can discriminate between the isotopes of gallium that come off. So we disregard the primary, I think it's gallium-69 that we use. We disregard those because those are primary ions. So it's an amazing tool, actually. It's actually been developed more for looking at geological samples, but we've adapted it for semiconductors. Yeah, that's it. Thanks.
Well, that's it from Charlie for now.
Right.
So,
thanks very much.
So now, after 4 presentations from researchers, we're going to go on to our let's call him a wildcard presenter for this half of the showcase. Instead of a researcher, we have a industry representative. We have Ashley Barker from Petrotech, the founder of Petrotech and ProBlogic.
Just click the button. Awesome. Well, thanks very much for that. So yeah, I've taken the road definitely not well travelled since I left uni, which makes me a wild card. I think I was always a bit of a wild card, and I'll show a few pictures of that. I have been a bit entrepreneurial, built up a few companies and things since I left uni. And I'll give you sort of a bit of a rundown on some of those. So this pretty much sums up my workday. Do I hit go to make that play? Maybe. I'll wait for the music to finish. That stopped. Awesome. So basically, we made up a robotic arm because we needed to move radioactive materials around. That's not actually the one that's been used on radioactive materials because people wouldn't approve of that. But yeah, and it's going again. Great. But yeah, so we built a custom robotic arm. We can control it remotely, and it's to load radioactive materials into our CT scanner. So I'll go into that in a little bit. Stop. There we go. So when I was at uni, this is my little crew up here, and it looks like maybe I couldn't afford trousers that actually fit me. But I did a lot of crazy things and got a lot of sour looks from a lot of lecturers by blowing things up on open days and launching rockets and all sorts of crazy things. I did my honours project with the Centre of Science doing underwater vehicles and writing the code for that and designing that sort of thing. It was a lot of fun. And it kind of set the stage for some of the things that I then got immediately into. So, nope, I got nothing. Oh, there we go. So I formed a company called High Tech Laboratories that then became High Tech Corporation. Terrible names for companies. Don't ever name your company like that. My business partner, Anthony, who I'm still business partner with, we built that together, and it's all about professionalism, you know, like, yeah, absolutely. We got ourselves an office. That's sort of a view of the office. You can see me in the corner there. Real professional outfit there. Yeah, it gets better. Nothing goes according to plan, ever. And this was sort of one of the great examples of that. Well, there we go. We got ourselves our first employee. You can see shoes were optional. Definitely a HS&E nightmare there. And we built a bunch of instruments used for downhole mining, like mainly for core orientation used in diamond drilling. So that's our first production run of a bunch of core orientation devices. You can see. Oh, is it? Is it like optical, is it? Ah, there we go. So on the left-hand side there, that one there, you've got a downhole magnetic survey probe we built as well. There's our core orientation devices all ready to go. More magnetic survey probes, except this time all in the housing. We built calibration rigs like this one in order to be able to calibrate our devices, and that's out in a tank in the middle of Jinjin where there's no magnetic materials around to go and mess with us. And finally, there's a bit of a dark picture, but me out on site training the guys how to use it. So that was sort of the first product that I managed to commercialize. We then realized that there was because we were doing a lot of work with a lot of different companies solving unsolvable problems. That was sort of our mandate. So we did work with Woolworths and people like that. You wouldn't think they'd have unsolvable problems, but they got all sorts of things. And when you start asking questions around the place, you find a lot of opportunity. But one of the things we recognized, there was no one out there doing a good job of radiation safety. And particularly at the time, this was about 2007, Uranium exploration was starting to be a big thing, and nobody was managing it well. And so we formed a company called Radiation Professionals. Again, terrible name of a company. We went out there and basically hit the market with training, hit the market with consulting service, basically a one-stop shop. We hired out equipment and everything that was needed to do radiation safety. And we had that background because we've got physics degrees. We were able to sort of just walk into that space, which was kind of nice. That there is one of our guys out on an oil and gas rig measuring radioactive contamination scale inside a pipe with an instrument that we made. We custom made the instrument. So what happened with us is we were in the uranium exploration field, but the bottom fell out of that about the same time as the GFC. And so we needed somewhere else to shuffle into, so we pushed ourselves into oil and gas, and that was actually a really good move for us at the time. That way. So I think I've skipped a slide. Yeah. About 2011, my wife was pregnant and I was about to, get a lovely daughter, and life was quite stressful. So I thought, what should I do? Buy into another company. That's a great idea. So I bought into ProbeLogic, which runs in Europe as Sonowave, and we repair medical ultrasound probes. So when I bought in, it wasn't really doing much, but did a whole bunch of R&D, built a bunch of equipment, developed a bunch of processes so that we were able to really be the leaders in the world at repairing medical ultrasound probes. And we've sold many franchises where we replicate our entire operation from our Perth lab and just replicate that into different countries. We've got 8 different centres now around the world, soon to be 2 more with any luck. No, that way. Oh, no, got it. So there's a picture of someone, see, we're starting to look more professional by this stage. Someone repairing an ultrasound probe. I don't actually think they're repairing it, I think they're posing for the photo, but you get the idea. That's a 3D ultrasound probe, so when someone gets pregnant, you get those lovely 3D pictures of babies. That's the back end of the sort of probe that takes those sorts of images. So just views of different employees doing things. You can see we're starting to look a bit more professional, a bit more laboratory-like. The fellow down the bottom is putting together equipment to go to one of our franchises. So we produce a lot of in-house testing equipment where we can take different probes made by different manufacturers, plug them in and test different parameters on them in order to determine where the fault is so that it can then be repaired. There's me, being an idiot, directing workflow or something. There's one of our testers, so we make lots of testers that look like this. We don't really worry too much about the aesthetics. It's literally just about functionality on a lot of these sorts of things. So probes can be plugged in. We can log into them remotely and be able to assist people around the world to fault find problems that they're having. This is one of our more recent developments. This is the brain board for a new type of tester that I can't really talk much about. But you can start to see the electronics are looking quite fancy. It's more like you'd expect to see on a motherboard of a computer. And Charlie had the question of, why do these things have to get smaller? Why do they have to be so small? That main chip that you see there is an FPGA. It's probably 25 mil by 25 mil, something like that. And we've spent a lot of time with a lot of irritation because the time it takes for signals to get from one side to the other is really, really annoying when you're doing high-speed stuff. So the speed of light is a problem. So getting those chips smaller makes that better and we can go faster. So on that chip, we take gigabytes a second of data. We need to dump that out into the RAM chips that are around it for temporary buffering. And a lot of the time, just because of the speed of light, we end up getting bits swapped just because they arrive at different times, which is really annoying. In 2014, we made another company called Petritech to specialise in subsea instrumentation, so oil and gas, scanning of pipelines and that sort of thing. We've even got shirts, which makes us extra professional. So this here is an example of why we made the company. We actually built it around this product. You get subsea pigs, and they're a device that goes in a pipe and they're basically like a plunger. You pump it down the pipe, and it can measure things. You can put smarts on it, or it can just be a dumb pig that cleans out the pipe. But either way, if you get that stuck in the pipe, and you're pumping millions of dollars of oil down that pipe each day, and you've just blocked it, that's a bad day for everybody. So they like to know
where these pigs are at any time in case they get blocked. So our solution to it was to stick a radioactive material in there on their pig, and then we made these devices that go on the outside of the pipe, subsea. Those ones are photographed there at 1,500 metres of the ocean. And when the pig goes past, the devices measure the blip in radiation, and that counts that a pig has been passed. So you can put a whole bunch of these along the pipe at different increments, and you can see the pig's gone past here, gone past there, hasn't gone past this one, we've got a blockage between there. Then you can pick the device up, run it along, and find out where your pig is blocked. The nice thing about doing it with radiation is it doesn't break, it doesn't turn off, it doesn't run out of batteries. There's acoustic pingers and things like that, but they suffer from those sorts of problems. And if you end up getting it broken, it defeats the purpose. Whereas we know that radiation source is going to be on for many years to come. Doing that subsea pig tracker got us the attention of a billionaire based in the US, and he funded us to make a subsea CT scanner. So that's what that is. We built it all from scratch. We made our own detectors, we made our own electronics for everything, and we redesigned the way CT maths works to get better images in our scenario. Because we're dealing with incredibly dense materials versus medical CT scanner, because we're going through steel pipes, beam hardening and scatter are huge problems, and our maths helps to reduce a lot of those dramas. There's me taking a selfie next to our test tank with the unit, so that's now completed and ready to go on its first job. We're hoping the first job will be in June, which means I get to go to Texas, which is COVID center of the world. Wait for that. There's an example of some images of like a pipe in a pipe, which is a difficult thing normally to scan with ultrasound or anything like that. We can just scan through anything, it doesn't matter what's there. So here's the actual robotic arm that's being used to load or remove the source in this case. Yeah, so you can see that comes in. The radioactive source is actually quite small. It's a bit terrifying actually. It's only 8 millimeters long and 6 millimeter diameter stainless steel pellet. But there's no way I'm going in that room when that's out. To put it in perspective, it's not as big as a lot of the sources that are used in industry, but if you picked it up and you put it in your pocket and you walked around for 15 minutes, you'd have some very serious problems, like you'd need to have most of your bum removed because all the tissue's going to be dying and things. So, reasonably serious source. So I guess the question is, what do I actually do? I do a lot of software development. We work across a lot of different languages, Python, embedded C, just about everything. We'll even use MATLAB. So we sort of pick a language for what we're going to do, and we're reasonably capable across a large amount of different languages. You meant to ring that bell. I do a lot of electronics development. Not so much myself anymore. I sort of have someone who does that for me who's much, much better at it than I am. But I still get involved from time to time. I do a lot of CAD and mechanical design. I like to do all of that myself, so I completely drew that CT scanner myself, because it's a good opportunity when you're drawing the CAD to actually brainstorm and get a lot of ideas at that point. We do huge amounts of maths. Pay attention in maths. It's a great unit. Do well at it, because you will use it if you do anything technical. And we do a lot of solutions development, so nothing ever works right first time, but we've got to make it work. I do a lot of the business side of things, and that's the less fun side of things, but it's a bit necessary. And if needed, I'll sweep the floor, so no one's above sweeping the floor. What did physics teach me? I think physics is a way of thinking. It's a mindset that you can apply to your life. It teaches you to question everything. I drive my wife insane because every time there's anything, I've got to question how it works, why it was done. She hates it. We learn how to solve problems, even if it's not a physics problem. It might be a business problem, or it might be some problem in your personal life. It teaches you a mindset that works across the board. But the biggest thing that physics doesn't teach us, that I want to sort of project to you guys, is learn to finish. Because in physics, you're taught, 85%, that's a high distinction, you've done well. 85%, when you're making a product, if it only works 85% of the time, that's terrible. That's an epic fail. If you're, also if you're like working on something, whether it be building a product or it be going into a sales meeting and you've got to do some work, thank you, you've got to learn that if you work on it to 85%, that's not good. You've got to finish what you start, and I think that's an important lesson. Cool, thanks.
So I was interested enough in that presentation that I missed the 12.5-minute mark. So that's probably a good sign. So do we have any questions from the audience to start off? I have one here up the front.
I think, I don't know how many engineers here, but engineering's easy. You can pick that up easy. It's the physics part that gives you that's the real crux of it. No, I'm kidding. But you can get people involved who have those engineering skills. They're quite easy to find. To find people with the physics and maths is more challenging.
So we had a question at the same time out the back here.
We built it and then coded it. We did the whole lot ourselves. The reason we built the robotic arm from scratch and not bought one off the shelf, because there's a lot of arms that you can buy off the shelf, is nothing really had the spec that we needed. So we wanted something reasonably cheap that would lift sort of up to 5 kilos, whereas everything in the sort of low-end market for robotic arms won't lift over about 0.5 kilo. So yeah, we thought it was a reasonable job just to make it ourselves.
Now I saw another question up this way.
We do. We take on a few students each year. So I've got 3 students this year. But yeah, a couple of the guys that work for me, I think 3 of them started as interns and then they rolled into actual jobs. So yeah, we definitely do that sort of thing.
Or else do we have questions? We'll take the question right up here.
It's mainly cobalt because it's a high energy isotope. It's got a photo peak at about 1.1 MeV, which is quite high. And that's convenient for us because we want to punch through a bunch of steel and concrete. The higher the energy we can get, the more that happens.
So I saw a question from Gabe over here.
No, I jumped straight out of uni. I worked as physics tech for a while, setting up the labs and whatnot, and then I jumped straight into doing something, and I, did everything wrong, but it's a good learning exercise. No, I actually started a little bit before him. He joined me after probably 2 years, something like that. Yeah. Not a huge capital investment, which was good because I had no money. But taking the plunge is actually a lot easier at a lot of you people's age where you don't have houses and families and children that all need to be fed, mortgage paid and things. If you want to go self-employed, try something soon before you go and get all those commitments because as a student you're used to living on nothing and it's easier to do at that time.
How are we looking on the stream? Do we have any questions there? Still nothing? Okay. So, got another question up the front? Okay.
I think the biggest thing is get out there and talk to everybody and make yourself known. And yeah, I think a lot of people, that they make some amazing tech or they do something and then they keep it really secret and they don't go and tell anybody, and that's not helpful. So just get out there, talk to people, find out what opportunities are there. There's so many opportunities out there for this sort of thing. You just need to go and find someone who maybe will put some money up for it or that sort of thing. Well, I still take on students, but I haven't got a lot of connection with academia as such. Something I'd probably like to do is get more connections, because I think it raises your profile, and I think you can get a lot of interesting science and tech come out of academia.
We'll probably end the question time there. I saw that the screen on that's flashing. Grabbed new batteries for it. That's why I ran off. So yeah, we will move on to the panel now. So that's not quite all from Ashley, because he's still here for the panel. So we're bringing back all of our presenters. We're bringing back Associate Professor Mark Pascovicius, Dr. Irene Suarez Martinez, Professor David Antoine, Professor Charlie Ironside, and we're also bringing up is it master's student? Yes, master's student Aini Ibrahim.
I'm Amy, and I'm a master's student with the Hydrogen Storage Research Group with Mark, and I have a project on using sodium borohydride as a way to store and export hydrogen in a renewable manner, and I'm basically just here to answer any questions on student experience.
So we've got 2 microphones for the panel because it's a big panel. So let's see if we've got any questions on materials science, on applied physics, or on student experience, or on science, or on industry. Basically anything that you think these guys can tell you about. So we'll go with Jordan. So I don't think that microphone is really working properly. So
This one working? Oh yeah, this one works. Yeah.
I think I was loud enough.
okay, this might be working now. Let's just see. Okay, yeah, that's fixed. We probably didn't actually capture the audio on that last question, but maybe someone else can just answer as well. Yeah.
Does it work? Okay. It's pretty loud. Cool. Yeah, so I can add to that. I agree with Renee. I never did my degree thinking that I was going to end up as a professor. That's something that just happened over time. So I did the same thing that Renee said. I went through, did an honours degree in physics, and then did my PhD here at Curtin, in fact. And I went abroad. I went to Denmark for a few years and did some research over there, brought some skills back here to Curtin again, and yeah, did these postdocs and ended up in an academic role doing some teaching and also research as well. And yeah, I mean, it's different to industry. The experience has a little less flexibility, I guess. You don't make the decisions yourself on what you're researching day to day. So that's one of the benefits of being in academia. We get to choose what we like to research. Yeah.
Maybe I can add, our experience, we can tell you about how we get there some time ago. The thing is, the world is changing fast, as you know, so the expectation from universities, research institutes, or whatever, in terms of what a typical path should be for an academic might be quite different when you get there. So that's the difficulty to answer this question in some way in terms of, what the practical way to get there. It can change quite quickly. Of course, you need to get the good grades and everything and go through the master degree or whatever, but the way it would be seen by those who would become your employers might be a bit different now than from when we did it. In my case, for instance, I had a 3-year break between the end of my master degree and when I started my PhD. I did something else. I don't know, maybe if you do this in this world, you would be completely, eliminated from any possibility to go into the academia. I just don't know. That's the way it was possible at some time. Maybe now it's definitely no longer. So, well, the academic world, basically apart from the practical ways to get there, you still have to have some sort of a vision that you really want to get there. Because, that's a particular type of job, I would say. Saying this at the same time, there is more and more, probably now as well, connections between academia and the outside world, which was maybe not so much the case 10, 15, 20 years ago. So even if you go into the academia, you will have, and you will probably have to develop all this connection with industry, with state departments, with governments and everything. So that means you won't be, isolated into your little academic world, or at least that's something you should try to avoid.
Just try to make sure that the mics are pointing away from the speakers.
Yeah, I'd just like to add a little bit, in as much as I had a fairly traditional academic career. I think one of the break points is after your first degree, deciding whether you want to do a PhD or not. That's a key step. That'll take you in a different direction. I quietly set up a research group. We were working away in the 1990s, quite happily doing what we were doing. And it turns out the dot-com boom came along. That's probably just before most of you guys were born. So that was around about 2000. And it turned out we were working on stuff that people wanted to invest in. In fact, they wanted to throw money at it. That was very interesting for my students. That was a huge opportunity that just emerged. What I would say is, you have to have the prepared mind in order to take advantage of opportunities. So what we were doing turned out to be very useful. And I think increasingly you'll find that high-tech stuff, as we heard about from Ashley, you're going to need this sort of academic industrial collaboration. If you have centres of academic excellence, often high-tech industries emerge from them. And that's a model that's been very successful in the last 30, 40 years or so.
So let's just try to move on to another question now, just because we don't want to just use up all of our panel time on one question. So we're running a little late, so we'll probably only go for 7 more minutes because we're already at 12. We're already past 12 o'clock. So let's try to see if we've got any other questions from the audience. We've got one right here. So the question was for the people watching on stream, because they couldn't hear that, have there ever been any real language barriers in your work? So I guess I think first I'll throw to Ashley, just on the grounds that he's worked in industry, so he's probably worked with a lot of people in different countries.
Does it work? It does. So I've not gone and actually worked overseas for an extended period of time, but I've done a lot of business overseas. And yes, sometimes it can be difficult, but strangely enough, people overseas are always really accommodating, and they do their very best to understand English, unlike what we do here. And so I found it is actually kind of fun. And you get to go there and see their culture and enjoy their food, love their food. So I've not had a problem.
Anyone else would want to add to that?
I work 2.5 years in France. I'm Spanish. I knew zero of French. So I was a bit scared because I don't speak any French. Normally the laboratories, or in my case the research center where I work, people spoke English because they were researchers, they write papers in English, they go to conference in English. So what you have to do is I have this theory that that's how I learn English as well. You learn a language by suffering it. So you go to the country, and that makes you learn at a speed that you will never guess in any other place, because you have to. So yes, you just go there, you find a program where they teach that language, and then you just practice because you have to. You need to buy food, you need to rent a house, you need to do these things. So you will learn. It's just part of the experience.
I'll just add to that briefly. I went to Denmark, and in Denmark they speak perfect English, like 99% of people. So I never learnt the language. A few curse words maybe, but nothing serious. So it wasn't a problem for me, but we're very lucky speaking English as well in the academic world. Yeah.
Maybe a quick comment, behind the, difficulty to learn a language or whatever, and as you can see, it's still a bit of a challenge. The language is really what makes you think, and your vision of the world and everything is deeply connected to your language. So that's where I see sometimes the difficulty in really understanding people from other countries, culture, or whatever. Okay, you can quickly learn the language relatively well, go on with your life, and that's okay. But then when it comes to, working with people and understanding how they see things, how they work, that's where you need probably way more time to really have a deep connection with, I speak from experience, I guess.
So we've probably got time for one more question. Do we have any questions from high school students who want to know anything about university life? No? Okay. Any other questions about anything else then? Got one up here.
This is mostly directed at our master's student. What inspired you to go back to study half your bachelor's, and how do you stay motivated?
That's a good question. So I guess for me, I did some research projects during my bachelor's, and after doing those, I really enjoyed doing research. So doing my master's was a decision so that I can, I guess, do 2 more years of research, and I'm still not sure what I'm going to do afterwards, but it's a way for me to keep going and do what I'm enjoying. And I guess how I stay motivated is because it's in an area that I'm interested in, and I think it's important to choose something that you are interested in.
So we'll probably end the panel there. Unfortunately, we've had to have a very short panel because we were running a bit behind. We now have a networking lunch now that's in front of the engineering building. So if you're a high school student, just follow everyone else. They'll be going in the right direction. We've got a sausage sizzle, and I don't know if there are any other options because no one's told me. But you can go to the networking lunch. You can talk to anyone who's there. If you'd prefer not to do that, then in here we will be playing an interview with Paul Hancock, who couldn't be here today because he is, I think, on holiday, potentially. So yeah, that's on the Kessler effect, which is an astrophysics phenomenon, and was a good preparation for the second half of the showcase, which will be on astrophysics and theoretical physics. So can we thank our panel, and then we'll... So we'll finish up here for now, and we'll see you at around 1 o'clock. Hello physicists, and welcome to another episode of Curious Conversations. Today I'm joined by an applied radio astronomer who has recently been conducting groundbreaking research into the Kessler effect. He is also a lecturer in first-year physics at Curtin University. Welcome to the show, Dr. Paul Hancock.
Thank you, glad to be here.
So, Paul, I mentioned in that introduction that you've been doing research into the Kessler effect, proposed by Donald Kessler in 1978. Most recently, you're the second author on an article titled The Development of Non-Coherent Passive Radar Techniques for Space Situational Awareness with the Murchison-Wide Field Array. Bit of a mouthful, but well, most people have an abstract idea of the Kessler effect from the 2013 film Gravity, with all the satellites breaking down, but we don't really understand it. So would you mind explaining what the Kessler effect is and why it's significant?
So effectively, the Kessler effect describes a a runaway situation in which you have a lot of satellites and debris that are in orbit around the Earth. And as you add more and more satellites to the equation, the likelihood of any two objects colliding with each other is going to increase. Now, the problem is that when two objects collide with each other, they create a large cloud of debris. And so you get more space junk and more space debris, further increasing the likelihood of future collisions. So the problem is that even very small pieces of space debris, things that are only about as big, as like a centimetre or a couple of millimetres across, can cause catastrophic damage to satellites, to astronauts if they're out and about doing their thing. It can punch holes in the space station, it can break communications arrays, and it can destroy solar panels. So the Kessler effect describes a situation in which you have so much material in a particular orbit that as soon as you have one little collision, it creates more objects, which then create further collisions, and you just get this runaway set of collisions where everything that's in that orbit will essentially just be turned into space debris. There'll just be so many of these collisions that everything gets completely wrecked. So the worry that we have at the moment is that there is so much debris in space. In fact, most of the objects that are in orbit around the Earth are actually either defunct, i.e. not working experiments and satellites, or they're just pieces of debris, rocket bodies, broken up pieces of previous satellites. So the worry at the moment is that even though we're not at that tipping point yet, thankfully, that if we don't do something to mitigate the effects of putting new things into orbit, then we're going to have to deal with the Kessler effect eventually.
So there's enough stuff in orbit that, would you say that like something of this size, really tiny, could potentially just break down an entire satellite and that satellite?
Oh, definitely. And something like this size, this actually, it looks like a piece of plastic junk, but it has a little bit of heft to it. And so this is going to be particularly dangerous. Things that are orbiting in low Earth orbit are traveling at tens of kilometers per second. And so these very high velocities, even with such a small mass, represents a large kinetic energy, which can then, you dissipate all of that into a small part of your spacecraft. Bye-bye spacecraft.
But in detecting this space debris, you used the Murchison Wide Field Array in your research to survey satellites in specifically low Earth orbit.
Mm-hmm.
According to your article, the Murchison Wide Field Array is a radio interferometer with a frequency range of 70 to 300 megahertz. How is it possible that low frequency radio waves can be used for that?
Excellent question. So normally the way that we detect things in low Earth orbit, in particular, is we either use optical telescopes, so we just look for the sun reflecting off satellites and space debris in low Earth orbit, or we use radar technology. So the same sort of radar that you would have at an transmitters, beamed in the direction that you're interested in, and you're looking at the reflected signal. The radar that we would usually use operates at a few gigahertz, which means that the wavelengths of that radiation are sort of, a centimetre, maybe a couple of centimetres at most, which means that you can really focus on some of the smaller objects. People have not traditionally used low-frequency radio radar, haven't even really bothered to build them, specifically for looking for space debris, partly because the wavelength's so long. So at 100 megahertz, your wavelength is about 4 meters, and so you may expect that you would only see some of the larger objects in low Earth orbit. So what we've done with the MWA is we've set up a bit of a sneaky system, which is to use a bistatic radar, which is to say that your transmission station and your receiver are not co-located, so they're physically distant from each other. And moreover, we've decided to not use our own transmitter system, but take advantage of all of the many, many transmitters all around Australia, which are transmitting in the FM band. So anybody who's listened to radio on the FM channels from 88 to 108 megahertz, that's the Australian FM broadcast band, and we have a lot of radio towers all around Australia. They're all beaming their radiation out sideways to try and hit all of the people in their cars and houses, and for some of those radio stations, the radiation will leak up into space. It will reflect off a satellite or a piece of debris, and that radiation then gets reflected back down, and we can receive that with the MWA telescope. So that's a general principle of how what we call bistatic passive radar works. So passive because we're not actually controlling the transmit power. So that's a general principle of what we're doing. This technique is using essentially every piece of the puzzle in a way that it was not intended. So the MWA telescope was designed to do astrophysics. It was designed to explore the early universe. It was designed to look for exploding stars and to look for supermassive black holes at the center of galaxies. And we've decided that all of that distant, faraway stuff is not so interesting, and that we'd prefer to look very nearby, to look at objects that are only, a few hundred kilometers from us.
Because you're looking at objects that are so close, that's very easily applicable. And so how might that information actually be applied in order to mitigate or even prevent the growth of a debris belt around the Earth?
Okay, so what we have is, firstly, a whole heap of objects in low Earth orbit. And what we want to be able to do is firstly know where they all are. Okay, so for some of the objects, and this is actually only a very small fraction, some of the objects, they have onboard propulsion systems, and they're actually able to maneuver to change their orbital states. So that if there was, say, the ISS, for example, although actually it's not a good example because it's very heavy and it's hard to move, but satellites like maybe the Hubble Space Telescope, they have some very limited propulsion system on board. They can move very slowly to change their orbits. And so if we know that there's a future collision event that is possible or imminent, then we can tell these various satellite operators that they want to move their resources around. Most of the stuff that's in space is either finished with all of its propulsion, so it's run out of the gases that it uses to propel itself, or it never had any propulsion to begin with, or it's just a piece of space debris. So the strategy that we're taking at the moment is that we want to know where everything is so that we can predict collisions, and so that we can understand how close we are to potentially having a Kessler effect, a Kessler event take place. And it also means that some of the active mitigation strategies that people have developed, which is trying to deorbit and clean up essentially some of this space debris, that they know where they can put their resources to try and remove these things from space.
It's very interesting applications. But not every project using the Murchison Wide Field Array has such obvious applications. Many of the projects on the Murchison Wide Field Array are curiosity based. And so what is the value of that curiosity based research?
Well, I mean, curiosity itself is a value, is it not? So a lot of the projects that are using the MWA telescope are what we would say pure science, or some people call it blue sky research, which is the sort of research that you do, which is driven by a curiosity or a want to understand the universe, or in some cases even, I mean, some of the work that's being done with the MWA is to understand the instrument itself. So we have a whole engineering group who build and operate the telescope, and they want to understand how the telescope works. So there's a lot of different science cases for the MWA. Some of them have less direct day-to-day implications. So one of the projects that I worked on was the GLEAM survey, which is essentially a survey of the whole southern sky using the MWA telescope. We produced an amazing map of some nearly 300,000 radio galaxies. And that, to the everyday person probably isn't particularly interesting, but it does add to our general understanding of the universe. And what tends to happen is that our need for understanding of the universe, our desire to explore, drives our investment in the telescope technologies. So some of the things that we're doing with the MWA telescope are very new in terms of the technology that's being developed and demonstrated, and this is then having applications into things like mobile phone technology. So the 5G technology that you have in phones now, one of the big advancements there is that the little tiny receiver is actually now a directional receiver and sender of information. So instead of broadcasting your phone signal all around the place, hoping that it's going to hit a tower somewhere, your phone can actually know where that tower is. The tower can know where your phone is, and they can beam their radiation at each other. So you can use less power, and you can also have, essentially, it ends up meaning that you can have a higher bandwidth for your mobile data usage. So that is sort of like a less direct link between the developing the telescope that we want so that we can do the astrophysics that we need requires that we have a telescope that sits on the ground and can electronically steer itself across the sky. Those same ideas and technology can be put into our phones to help us in our everyday lives.
So do you just end up with tangential applications, like how quantum mechanics would have been applied to produce colors in phones, on phone screens and that?
Yeah, so a lot of the applications are tangential in that way. They're sort of, you're using the funding for blue sky science to build instruments, and often these projects are not just use an existing instrument to do something useful, they're developing new technologies. And the technologies will be developed for, taking photos of the night sky. And in fact, that's where some of the first digital camera technology came from, was people wanting to image the sky in a very sensitive way, and not have to use, chemical emulsion on glass plates and things like that. So so there are many sort of knock-on effects like that that occur. And then every now and then something amazing happens and we discover, relativity or the gravitational waves and things like that, which probably has a more direct link to our everyday lives.
So all of these amazing discoveries can be done using the Murchison Wide Field Array, and yet it's expected to be superseded by the Square Kilometre Array in the late 2020s. Mm-hmm. What makes the SKA such a significant step up from the MWA, and what kind of impact might its observations have on radio astronomy?
So the SKA telescope, the Square Kilometre Array, is designed to be effectively two telescopes in one. There's a mid-band telescope which is operating at gigahertz frequencies, and then there's a low frequency component which is going to be operating at low frequencies, surprisingly enough. And the MWA is a precursor instrument to the SKA low, which means that a lot of the technology that we're developing for the MWA is with a forward look to say we need this technology in order for the SKA to work. So back in 2000, I think it was, the early days of the SKA, they had these grand plans of we want a telescope that can meet these science goals. And at that time, there was no technology available to build that telescope for less than, I don't know, the total economy of the Earth or something, right? So part of the SKA plan is we have these grand science goals that we want to meet. In order to meet those goals, we need to develop the technology, so hardware technology, but also software technology, data processing, workflows and things like that. These all need to be developed to make the project possible and feasible. And so the MWA is one project that is along the line of trying to demonstrate technology for the SKA. And the other thing is that the SKA, as compared to the MWA, is going to be a much larger and much more sensitive instrument. So the MWA is made up of 128 tiles out in the Murchison Desert. I don't recall off the top of my head what the collecting area is, but it's nothing like a square kilometre. So the collecting area of the SKA is going to be enormous, and that means that it can have a very sensitive view of the radio sky. Not only that, the SKA is going to be much more distributed than the MWA. So the MWA has a lot of tiles that are very close to each other, which give us a low resolution view of the sky. And they have a few tiles that are maybe up to 6 kilometres apart, which gives us a slightly higher resolution view of the sky. The SKA will have stations, they're not tiles, they're stations, that will be distributed all around Western Australia and even into other states as well. So there'll be much, much longer baselines in the SKA.
There are a few in South Africa and New Zealand as well, aren't there?
Yes, so there will be, for the low frequency, it will be in Australia, and then the mid frequency will be in South Africa. So there's that sort of split telescope design. The two parts of the instrument, you won't combine their signals together directly, but of course what we always end up doing in astronomy is we take information from the low frequency, the mid frequency, we add in a bit of optical data, UV, gamma rays, X-rays, everything that we can to try and build this complete story of the universe and of the objects that we're looking at. So yeah, so the SK will be a mid-frequency radio telescope in South Africa and the low-frequency telescope in Australia. That low-frequency component will have very long baselines, which will give us a much higher resolution view. So the advantages over the MWA will mean much higher resolution and much more sensitivity. But we need the MWA, again, as a stepping stone, and this time as a scientific stepping stone along the way to the SKA, so that we can use the MWA to understand what the sky looks like at this low sensitivity, low resolution, so that we can actually calibrate the SKA telescope. So you sort of need to know what the sky looks like a little bit before you can then go out and start making images of the sky. It's a little bit of a circular process, but yeah, that's how it works.
So given the significant increase in the resources available, what kind of problems do you think that the next generation of astrophysicists will have to solve?
So astrophysicists at the moment are primarily focused on actually answering astrophysical problems, but more and more what is happening over time is that astrophysicists are having to become more data scientists. The volume of data that we are capturing, even with the MWA telescope, is terabytes per day, terabytes per hour in some cases. And so we need to have the hardware, the software to be able to process that data. But these are instruments that we effectively built ourselves. There's no MS radio telescope or something that we can just get from Microsoft. So we have to develop these software tools, and we need astronomers with the astronomy and astrophysics knowledge to be able to say, yes, these tools are doing the right thing, but we also need people with software expertise. So one of the biggest challenges that I see at the moment is that we have a lot of amazing physicists and radio astronomers who are working on these projects, and we really vitally need more people with more computer science expertise, more coding expertise, who also know something about radio astronomy.
You lecture Physics 1 and Physics 2 at Curtin.
Actually, at the moment, only Physics 1.
Only Physics 1, okay.
Sorry, should have let you know.
So how do those units and a physics degree at Curtin help students cultivate the skills like programming skills, like data management skills that you've mentioned, and prepare them for a future career?
So the physics courses, the physics curriculum that we have at Curtin, it includes not just your standard physics courses, but there are also computing courses that are built into each of the different streams of the physics major. And we've put those computing courses in there because no matter what career you will look for in the future, no matter what stream of physics that you're interested in, computing will be a vitally important skill to have. So we recognise that, and so we've embedded that into many of the curricula. Moreover, we've just starting last year, we've had an explicit high-performance computing course that we've developed for the honours level. So all the students who are doing honours at Curtin now in the physics degree are now recommended to do the HPC course, and so they'll gain skills in GPU programming, how to use and create parallel architecture programs, how to deal with large data problems, and also how to orchestrate workflows as well. So that's one of the things that we're very keen to develop for all of the students here at Curtin.
Well, that's all we've got time for this episode. So thank you for that's interesting. That's all we've got time for this episode. So thank you, Paul, for agreeing to be here today.
It was a pleasure.
This interview is first premiering at the Curiosity Showcase, but there are more like it. If you want to see those interviews, search for the Curious Conversations playlist. Just be sure to come back by 1 p.m. for the second half of the showcase. Or if you want other people to see our videos, please like, share, and comment below.
And until next time, stay curious.
Hello, is that working? Okay. Hello everyone, thanks for coming again. Just to start us off, again I want to wish to acknowledge the traditional custodians on the land in which we are meeting, the Whadjuk people of the Noongar Nation, and we wish to acknowledge and respect their continuing culture and the contributions that they make to the life of this city and this region. So thanks for all for coming to this afternoon session. For those of you that weren't here this morning, again, I'm Jordan. I'm the president of the physics club for this year, and this is our one of our first big academic events, so thanks for your support and for coming. And I think we have a variety of people here, but it's good to see lots of perhaps some new faces from this morning, and then others have gone. But yeah, so this hopefully will give you a good insight into some of the theoretical research which is done here, and also the astrophysical research which is done here, which are two different streams, I guess, from what we had this morning, but hopefully you'll learn all about them today and you'll enjoy them very much. So before we pass the key on, I'll just pass to Angie and she can have a little bit of a talk.
Hey everyone, so I'm Angie, I'm from STEM Outreach. So for those uni students that are here, so unfortunately not the high school students, you can volunteer for STEM Outreach, and we have a really cool event coming up to help high school students. And if you're a high school student, you might want to talk to your teachers about something called the Science and Engineering Challenge, which is coming up in May. We've got some cool challenges coming up there. We need volunteers to help out. So I know a couple of you guys are already part of this and volunteering for it, but if you are a uni student, you have to be a uni student to volunteer for STEM Outreach. Type into your search bar Google Curtin STEM Outreach, and then go in and volunteer as a register as a volunteer, my goodness. So I'll leave you guys back to whoever, Jordan, Keelan.
So definitely something worthwhile signing up to for uni students. So on to the presentations for today. Our first presentation is on radio astronomy and exascale computing from the former director of the Murchison Wide Field Array until December of last year, and current director of the Curtin Institute for Computing, Professor Melanie Johnston-Hollett.
All right, thank you. Are you driving the slides for me, or am I driving them? I've got the clicker, so it's going to do it. Okay, cool. Let's see if it goes. Oh yeah, there we go. So we don't need to see the title. All right, so thank you for inviting me to come and speak to you today. I'm not actually going to talk too much about computing, except in how it's related to radio astronomy and how I came to be director of the Curtin Institute for Computation, having had a background in radio astronomy. So this is actually about some of the radio astronomy that I've been working on at the moment with my research group, who are actually still based in the Curtin Institute for Radio Astronomy in Tech Park. So, do I have to click twice to make this go? All right, so briefly, for those of you who don't know, radio astronomy commenced in the late 1930s, and so it's existed for about 80 years. And I'm sure you've all seen radio telescopes, and being here at Curtin, which hosts the Murchison Wide Field Array, you realise that radio astronomy is a very advanced field in Australia, but there's really a number of nations that got into radio astronomy after the Second World War. So they had a lot of people who had been working on radar, and they needed something to do when the war ended. And so these were the Netherlands, the United States, the UK and Australia. And in the late 70s and 80s, they had a peak of investment at a national level on building radio telescopes. So what you can see here is some of the first interferometers. So these are instruments that work in unison to create higher resolution images than you can get with a single dish radio telescope. So this is the Westerbork Synthesis Radio Telescope in the Netherlands. This is the VLA, so that's in the movie Contact if you've seen it in the United States. And this is the Compact Array, which was built in 1988 in Australia, in New South Wales. Now, in addition to building the actual antennas and the hardware, one of the things that they did in the 70s and 80s was actually worked on imaging algorithms and the compute that they needed to process the data they get off radio telescopes. So radio telescopes are big data machines, and although these aren't big data by the time of now, by the standards of now, they certainly, the future telescopes are. Now, about a decade ago, we had the start of what I call a radio renaissance, where we invested again, mostly at a national level, but also at an international level, on either upgrades to existing antennas or in building new arrays. So the first one here is again the Dutch building the low frequency array in the Netherlands, which is a low frequency telescope. So that's got different antennas, so dipole antennas versus these dishes. They upgraded the VLA, so it's now the Jansky Very Large Array in the United States. We upgraded the Australia Telescope Compact Array, and we built the Murchison Wide Field Array here in Australia, which was completed at the end of 2012. And as was said in the introduction, I was the director most recently for 3 years. What we didn't do is we didn't have those infrastructure investments correspond to the also investment in imaging algorithms and compute needed to do the science that we want to do, and so that's happening now. Okay, so just to tell you how much of an advance we've made and how much processing we need to do now compared to that first generation of telescopes. This is an image. I don't know how well you can see that. Can we turn the lights down? Is it possible? Very good. See, I don't teach here, so I don't know. Thank you. This is an image of Centaurus A, which is the nearest radio galaxy to us. So what you've got is there's a supermassive black hole in there, and it's spitting out lots of electrons which are producing radio waves as they accelerate in a magnetic field. This image was taken with the Australia Telescope Compact Array by a woman called Elena Fayen, and I was on the project for this. And we spent 3 years getting the data for this image. So this is the size of an individual image you can make with the compact array. So we had to make a mosaic. We had to point the telescope in multiple different places. We also had to use different configurations. So 3 years to collect the data. There's actually 423 of those pointings required to make this image. It then took 2 years to get the compute to actually make that image and put all those things together. So this is a long sort of process. So it's 5 years to make that image. Okay. This is 2 minutes of data with the Murchison Wide Field Array processed by Ben McKinley, and I think originally this took Ben a few months to do because he was coming up with the processing algorithms and workflow. But you can see we're basically looking at a larger field of the sky. It's not taking us years to collect the data, and we're needing to process it relatively quickly. So that's why we need to advance both compute and algorithms to be able to do radio astronomy. Also, this field of view, you can no longer approximate it to being flat. It actually is curved, and so you have to deal with curvature of the sky, you have to deal with problems with the ionosphere, all sorts of stuff. The ionosphere causes radio waves to bend and scintillate, just like you see optical twinkling of stars, and we have to correct for that, and it happens in different places on the image, so you have to do direction-dependent corrections. So that means you need a big matrix, you need to do a lot of stuff. All right, anyway, so we're advancing with our hardware. We need to also keep up with the compute. Come on. Right, now, I was asked in this brief to talk about some of the work that I'm actually doing, and so I'm going to actually talk to you about searching for the cosmic web. Does anyone know what the cosmic web is? Vaguely, well, Kath does, as we'd expect. All right, so if you could sit outside the universe and look into it, matter is not distributed isotropically. It clumps together in a web-like structure, which we call the cosmic web. And these are actual observations taken of the position of the nearest, I think it's 500 million optical galaxies, and so it's showing their position in the sky and a slice of the sky and their distance from us, measured with a Doppler shift. So that's really what the galaxies look like. They're distributed in this sort of web-like structure. Now, in between those galaxies, we expect to see radio emissions. So if you've got structures like this, these are actually clusters of galaxies, so you've got sort of hundreds of galaxies mushed there, hundreds there, and then big long filaments connecting them. And that we should see both as chains of this web here in the optical, but also in the radio, because there's a very low-powered magnetic field here, or a very weak magnetic field, and there's electrons spiraling in it, which gives rise to synchrotron emission. So we're trying to find it. Now, so here's just another simulation done again on a supercomputer. This is actually quite old now, done in Germany. And so this is what it would look like if you could take a God's eye view of the universe. It's this sort of spiders on drugs kind of web thing. At the intersection of these big long filaments, you get hundreds of galaxies sitting in a gravitational well, and they produce things that look like this. So this is a radio image, composite radio image of a galaxy cluster, which has got the very unexciting name of Abell 3888. And what you can see in the blue is radio emission from the MWA, so this is diffuse, plasma, and all these little dots here are individual galaxies, and there's hundreds of them sitting in there, this hot plasma, which we can detect. Now, what we're trying to do, that's lovely, is we are hoping to find the structures that come out of this thing, these very faint regions of the cosmic web, very low surface brightness diffuse radio emission. All right, come on. Okay, and this is a simulation done on the Pawsey Supercomputing Centre, or at the Pawsey Supercomputing Centre by my student. How do I make the video play? There we go. Of what that cosmic web looks like in the radio should we be able to detect it with a radio telescope. So what you're seeing here, there's a galaxy cluster. You can see it's sort of shell-like, and these are from shocks, accretion shocks that happen as matter falls in to the gravitational well of your galaxy cluster, or along the filaments themselves. So this is from Torrance's paper. So Torrance is a PhD student here at Curtin. Right, another reason you need a supercomputer. Now, back to this wide field of view. So there are two ways you can try and find the cosmic web. You can either try and image it directly, or you can try and do it statistically. To be able to do it statistically, you want to cover the whole sky. So the MWA is really good for this because it's got a huge field of view. So this is this image of Centaurus A, one single pointing with the MWA I showed you before, done by Ben McKinley. This is the full moon. This is the size of the full moon here. And so this is the whole sky. You can see one pointing of the MWA takes up quite a fraction of the whole sky, which means you can make beautiful images of the whole sky, like this, relatively quickly. So you can do surveys of the whole sky at low frequency. This is an image done by Natasha Hurley-Walker, also from Cairo, in 3 radio colours using the MWA. So this is a galactic plane through here. All of these little dots are supermassive black hole hosting galaxies. So they're radio galaxies, and there's more than 300,000 of them in this image. The cosmic web should be buried in that. So we tried to do it directly to start with. This is a very low resolution image made with a telescope in the northern hemisphere called the Sardinia Radio Telescope. And if you can see, this is from 2 hours all the way up to, I think it goes up to 10. So this is a huge piece of the sky, very low resolution. And what we're trying to do here is find that diffuse low surface brightness stuff. Each of these little blobby things, these are galaxy clusters. There's hundreds of galaxies in there. So this is a filament, right? So we got really excited. Valentina, who led this study, got excited and said this was the first direct observation of the cosmic web, all this sort of diffuse stuff here. And she observed it also with another radio telescope, the VLA I told you about at the start, and got those blue contours, and so published this paper that said this is the first observation of filaments of the diffuse cosmic web ever seen. Right. We tried to replicate this result, as you should do with science, and we re-observed it with the MWA, and we got this. So this is a low-frequency MWA image. These are these same contours here in pink as in blue there, and you can see there's nothing in the MWA image. It's not there. Now, we did wonder, what was that? This was an image made by my PhD student, Torrance again, the guy who did the simulation. And I happened to look for some spectral line observations with hydrogen gas, and that's what it is. So here you can see the contours, here you can see a background image of hydrogen alpha emission, and so it just happens to be at the same frequency. It's a spectral line, so not the cosmic web. So direct imaging, no. All right, how about stacking? We'll try stacking. So this is a paper which has actually been submitted only about a month ago by Tessa Wernstrom, who works here in Perth at CSIRO. And what she did was find regions in that image of the sky I showed you with the MWA, where there were pairs of galaxy clusters, like this, and she stacked those images statistically to bring this very weak cosmic web signal up from under the noise. And she claims a detection. She says she can see in the regions that she expects between the pairs that there's some sort of excess emission. All right, we weren't involved in this study, but we're trying to replicate it. We're trying to see if we can find it, as you should do in science. And so the first thing that we've done is built a simulation. And one of the problems that we've had with previous simulations, like I showed you, is that they simulate the cosmic web, which is this stuff down here, all these little shocks and things, over a large chunk of the sky. So you can see this is like 4 degrees by 4 degrees on the sky. They don't put all of the radio galaxies. So all the radio galaxies are contaminating sources. And if you want to find it from real data, this signal, you've got to have both the radio galaxies and the cosmic web. So we've done that now. This is in fact the most sophisticated simulation of the cosmic web plus radio galaxies and radio halos, if you're worried about this stuff, ever done. Now, I've shown them to you in two separate parts because I want you to look at the scale. So don't worry about the units, but see this goes up to 2 of these units, Janskis per beam. This is here at 10 to the minus 6 Janskis per beam. So if we add them together, you don't see any of this stuff. That's how faint this is. Really, really hard. So what we've done is we've done 2 things. We've taken the process that she used on the simulation, or on the real data, and we've applied it to the simulation and said, can we find the signal? And the answer is no, we can't. And we're about to take this process and replicate it on the real data and see if we can find it. Now, the fact that the signal and her paper don't agree tells us 3 possible things. 1, she did something wrong, and that it's not really in the data. 2, we don't understand something about the universe when we're building our simulations. Or 3, our simulations are wrong. So we haven't got a definitive result yet, but there's some interesting stuff to follow up on. So this is a multi-year project to find something that's really fundamental but hard. Now, I didn't want to leave it there because that would be a bit depressing. Did we look for this thing? Yes. Did we find it? No. So I wanted to talk about one of the other cool results that we had along the way. So I introduced to you the USS Jellyfish, which is this object here, which if you've been paying attention to the recent media has had a press release about. So this is again work done by my PhD student Torrance. And this is a galaxy cluster. It's got the very uninteresting name again of Abel 2788. What you can see in the pink is hot X-ray plasma that we detect through the process of thermal Bremsstrahlung, which is where electrons decelerate when they approach a positively charged ion, and then they produce X-ray emission. And then what you can see up here is radio data taken with the MWA. Now this is a really weird source. So for a start, it's got this wonderful scale here in what we call kiloparsecs, which is not very useful. A parsec is 3.26 light years. So this is 600 light years. Sorry, kilo. So 6,000 light years across here, or more than that. So 6 times 1,000, so 600,000. There we go. These are big. In the background, you can see the optical galaxies, and then this fuzzy looking thing here is the jellyfish. This is what we call the steepest spectral index source ever seen. And what that means is that the radiation, which is coming from the synchrotron process of electrons spiraling in a magnetic field, is dropping off extremely fast with frequency. Faster than anything we've ever seen by a factor of 1,000, in fact. And so, hope this movie will work. So this is a movie made with the MWA. It's starting at 215 megahertz. And this is what this region of the sky looks like, and we're going down to 88 megahertz. This is my last slide, guys. So just watch. It's going to, hopefully, if it's going, here you go. You can start to see the jellyfish appear from the murk, the dimness. So as we go down to very, very low frequencies, this thing pops up, and it is super bright at super low frequencies. This is a truly weird thing, and we think this is a result of having 2 or more active galactic nuclei spewing out electrons into the intracluster medium and having a cluster-wide event, like a shock or something, come through here and gently re-energize them. So that's kind of cool. So you can look it up. If you look up USS Jellyfish online, there'll be news articles and things on it at the moment. All right, come on. I'm trying to advance. So, too far. So, takeaways from this. Radio astronomy requires the use of high-performance computing. You cannot really do the type of work that we do without it. So you need to invest in both your infrastructure and your algorithms. So if you're interested in radio astronomy and understanding the universe, that's great. But if you're interested in doing algorithms or understanding how compute works and using radio astronomy as an application, this is also a field that you can get into. And yeah, we haven't confirmed the detection of the cosmic web yet, but we have found some cool stuff along the way. So thank you.
So we have time for some questions for Melanie. So do we have any questions from the audience to start with? We have one right there from Sam, was it?
Yes, is the short answer. So there's a thing called the International Telecommunications Union, which specifies which bands you can have your telecommunications satellites and things emit in. Radio astronomy has some protected bands, but they're extraordinarily narrow. And the problem that we have is that we want to look over the entire radio spectrum. So yes, sources like that are things that we need to remove from our data if we can.
So we have another question from Jordan.
So you would expect some of the matter to be isotopically distributed in the universe. So why is it that we get some clumping here and there? Are there any possibilities?
Yes, so very soon after the Big Bang, there was a very, very small change in the way that matter was distributed in the universe, and then the Big Bang happens, and then that very small change in density, which I can't remember, it's something ridiculous like 1 part in several billion, generates everything that we see in the structure of the universe today. Maybe Kath or James have got a better argument for that. Yeah, there we go. Cosmology, yes, so that's well understood. Yeah, produces everything else. If you give that 13.7 billion years, you get everything that we see today.
So do we have more questions from the audience? A question from Ashley.
So there was infrastructure investments,
Yep.
in 2010. What's happening in the next 10, 20 years
With
investments?
That's a really interesting question. So the square kilometre array is coming, as I think probably anyone who's following radio astronomy knows. So that's going to be built partly here in Western Australia, in the Murchison, in fact where the MWA is, and also in South Africa. So that's a multi-billion-dollar project. The Australian government has committed $293 million to that, and we're going to deploy over 130,000 antennas up in the Midwest, and there's going to be around 200 dish-like array in South Africa. Now, that's the infrastructure investment. What you need to go with that is a series of data centres and high-performance compute resources globally to be able to deal with the data flow. And as far as I know, no one's actually put their hands up to pay for that part yet. But it is something that's under discussion. So there will be an associated investment to be able to do that. So the SKA will produce 157 terabytes of raw data per second for the instrument that's coming here in Western Australia. That gets mixed down to about a petabyte of data a day. So you need to be able to image that and interrogate it and then potentially store whatever you need to store out of that. So that's an ongoing international discussion, that part of it.
So we've got time for just one more question for Melanie, if anyone has one. Well, if we don't have any, then we will finish up there. So let's thank Melanie again. And unfortunately, Melanie, being an extremely busy person, cannot join us for our panel at the end. So we'll have every other presenter there. Including our next presenter will be there, and that is the head of physics at Curtin, Professor Igor Bray, presenting on quantum collision theory.
Thank you. It's a delight to be here. Thank you very much for organising all this, and it's gratefully appreciated. Thank you, all of you, students in particular, for coming. Unfortunately, I was hoping that one of our PhD students would also be talking today, but he is unwell. So I'll say perhaps a few more broader words as well about the physics course. So, is it ready to go? And okay. So I'm going to be talking more specifically about our research. It's work that I've been doing almost every day for the last 1.5 years, including the last few days. But a bit broader about the physics department, or physics and astronomy department we have. We have a rather unique combination of subjects or focus. We have a combination of mathematics, physics and computing as the major components of our physics degree. So much so that at the honours level we even have a course on high performance computing now. And that's a really unique situation around the world, and many of my physics colleagues around the world are rather envious that we have this. But as you saw from the previous performance computing, and in fact from this morning, high performance computing is ubiquitous. I'm going to talk specifically about the work that we're doing with colleagues at CERN, as well as ourselves here. The group of theoretical physicists here, apart from myself, is Professor Dmitry Fursa and also Lesha Kadyrov. And we've been sort of like the three musketeers that have been together for about 25 years. And we've done a lot of things together, and this project is one of them. So, motivation. Well, there's a couple of Nobel Prizes in physics to be had in this area. First of all, no one can explain matter-antimatter asymmetry in the universe. This has been the problem when I was a university student, and people were very keen for it to be solved sometime soon. Well, here we are 40 years later, it remains unexplained. And that's a statement that in this world we have a bit of antimatter, so enough to do things like cancer detection. If you've heard of PET scans, that stands for positron emission tomography. So we can use positrons, which are anti-electrons, to detect cancer. But the standard model predicts that at the beginning of the universe, matter and antimatter should have been made in equal parts, and that's clearly not the case in the visible universe, whether it be here on Earth or looking out into space. Furthermore, there is no unification of quantum mechanics and gravity. So those of you who watched Big Bang Theory on television might know that Sheldon's project was string theory. Well, even he gave up on that, right? And do you know what he got a Nobel Prize for in the last episode? For super asymmetry. Very funny joke for those of us, because there's such a thing called supersymmetry as a mechanism for unifying quantum mechanics and gravity. So super asymmetry makes no sense whatsoever, but it was a delightful piece of humour. But anyway, because we know that antimatter is governed by laws of quantum mechanics, we know how antimatter will react under gravity. If you drop it, what happens? Nobody knows. So, first of all, how do we come in? Well, our job is to calculate the most probable ways of making antihydrogen. So we'll start with positron scattering on atomic hydrogen. That will form positronium. The label PS is used for positronium. It is a bound state of an electron and a positron. And if we put a little star on it, that means it can be in an excited state. I'm going to show you this with some animations in a moment. And so we form positronium, then with time reverse this. We've put positronium scattering on either a proton, which is backwards, or we can replace the proton with an antiproton, because it really doesn't matter by symmetry. So the proton will bind an electron, and an antiproton will bind the positron to form antihydrogen. So I've used some words there. Now I'd like to show this to you with some animations. Okay. So let's see if I can. All right, I'm going to use this so it's a bit more visible. Perfect. Thank you so much. Okay. Well, we begin with just the hydrogen atom, not the ideal surface. Got it. One. Yes, here it goes. Okay, so this is an animation of a hydrogen atom. It has the key elements of discrete bound state. There's a countably infinite number of discrete states for a hydrogen atom. And the energy levels between the ground state, the ground state and the 2s excited state happen to be known to 15 significant figures. Phenomenal measurement. And the idea is to make anti-hydrogen and measure that same energy difference to see if we can find any asymmetry. So our job is to, this is not working quite so well, this is something to put underneath. Try if I can follow on your screen. Put my glasses on. Okay, we now have positron scattering on atomic hydrogen. You saw that was first case of elastic scattering. Then we're going to have excitation. That's another typical process. And another standard process of collision is ionization, so-called ionizing collision. But here's something interesting can happen. Because positrons to each other, you can get a binary system, just like that. And you have electron-positron bound state. And that's what we want to form. And I'm going to wait for it to happen, come around one more time. So there's once more with excitation. Okay, I've just paused it there. So now we have this positronium, and now I'm going to time reverse it. So imagine, so here you have a proton right now, time reverse it, and we'll have positronium scattering on the proton to form hydrogen. But we can go to CERN, because it's the only place you will get a beam of antiprotons, and replace the proton beam with antiprotons. And so we'll time reverse this. Comes in, and then that's how you form the atom. Now, for those of you who want to know what positronium really is, actually we don't need to. So, as it happens, the Schrödinger equation for positronium is the same as for atomic hydrogen, except that the center of mass is in between them, right at the proton. So positronium lives of order like 10 to the minus 9 seconds. You know, when matter and antimatter come together, they annihilate. And the goal is to create as much antihydrogen as we possibly can. So the first thing we need to do is we need to create positronium that's longer lived. And we're going to do that by laser exciting positronium to a higher excited state. So our calculations, and they're incredibly time intensive, so I've used 4 supercomputer facilities, ran out of time for over a year in just doing the latest calculations, and that includes the world's number 5 computer, Frontera, in Austin, Texas, because we try to calculate what's the high excited states that can be reached in both experiment and calculations, and to provide the maximum number of anti-hydrogen atoms can be done. If we can go back to the presentation. Right. Thank you. So that's what we do in theory, and in experiment. I'm not showing you the actual laboratories because they're absolutely enormous, but the idea in the experiment is laser pointer works perfect. With a positron beam, you create positronium. You then laser excite positronium to some high excited state Well, which state? Well, our calculations specify which is the best state to start your positronium with. Then you come across an you bring the positronium beam on the antiproton trap that is at CERN. It has to be very, very cold because we want to be able to do gravity experiments. So when we make that antihydrogen must be moving very, very slowly, right? Because if it's moving quickly, then of course you will never see gravitational effects on, say, the beam of antihydrogen. There's a hope to make a fountain of antihydrogen. So then you form the antihydrogen, and using an accelerating sort of electric field, you'll have a beam of antihydrogen atoms, and if you have enough of them, you can do experiments. And one of the experiments has been done already, and it's called a spectroscopy. It came out in Nature a couple of years ago, and I mentioned that, that the 1s to 2s energy difference in ordinary hydrogen is known to 15 significant figures, and there they are. Can you imagine doing a measurement of that level of precision? But the beauty of these precision measurements is then you can try and repeat them for antihydrogen so that you can compare. And they've measured the first 10 significant figures, and unfortunately they're identical. But there's 5 more. And so people are creating fellowships and asking for a lot of funding to see if they can get access to those 5 figures. Now, maybe it's time to say, well, perhaps this is not yet, this is not worthwhile persisting in this direction. Hard to know, but you know, first glance, one would think that the energy difference is not going to be a source of any asymmetry between hydrogen and antihydrogen. And people are now trying to develop or create sufficient numbers of cold antihydrogen. So with cold antihydrogen, there's an extra complexity associated with not just making the antihydrogen, but also cooling it. And a lot of technologies are involved in that space, but I imagine within the next 2 years, people will be able to definitively say of how antimatter behaves under gravity. Does it fall? Does it do nothing? Does it go up? Is there such a thing as anti-gravity? We are about to find out. So that's all for me. I'd be delighted to take any questions. Thank you.
So do we have any questions from the audience?
Keep talking about that sufficient numbers of antihydrogen. What sort of numbers are we talking?
In the thousands, so you want to, it will depend on what experiment you're doing, but typically it would be, minimum would be in the thousands for most of these experiments. Yeah. Mm-hmm. Yeah, so it would fall relative to the apparatus, which would be in the vacuum. So you mustn't have any interaction between matter and the antimatter you've created. All that has to be done in a very high vacuum. But you can create a beam, a slow-moving beam, and you know that a beam at certain speed will be hitting the wall, and you'd be detecting your hydrogen atoms or antihydrogen atoms at a particular part of the apparatus, and if it goes down, so sufficiently low, and of course it has to be well collimated, you have to be very confident that there's a significant drop or rise through that, but it must be done in the vacuum. Emission tomography? Yeah, so we use positrons for many applications. In our hospitals, all of them will have PET scans. Positrons are also very useful for analysing materials. They will find imperfections in coatings, for example. So the A380 paint work, which was done with many, many fine beams, that used a thing called PALS, positron annihilation lifetime spectroscopy, as a way of finding imperfections in the paint work. So antimatter has a lot of uses. People have proposed to use it in space propulsion before. However, the problem of collecting sufficient antimatter and keeping it for long periods of time, it remains a major problem. But many nuclear reactions result in antimatter positrons being emitted away, so beta decay, beta plus decay indicates positron.
So do we have any more questions for Igor? We have one, yep.
Yeah, so this will come from a major sort of nuclear reaction in interactions. I don't know the details of how it's done, but it can only be done at CERN because of the massive accelerator that we have there as a mechanism for generating antiprotons, which will be highly energetic in the first place, and then they need to be trapped, cooled, stored, all sorts of things that happen afterwards in a perfect vacuum.
We had a question up here in the middle row.
Yeah. So, in fact, not only does it take so long, but we are the only group in the world who can do them, who has the code, because it's incredibly complicated. These are two center systems, so it's hard enough to do an electron or positron scattering calculation on an atom molecule in a one center system, where the center of mass is at the origin, say, and everything revolves around that. This is a two-center system because you have the anti-hydrogen, and then you also have positronium, which has its own natural center. And combining coordinates and combining all of the mathematics around that is exceptionally complicated. And there was only two other groups in the world who had attempted this in the past, and both of those people passed away now, and who've been unable to take it to its logical conclusion like we have. So, but the expense is just absolutely enormous of doing these calculations. But that's what supercomputers are for. They're there to enable the new generation of problems to be solved.
So just to follow up to that one, you're talking a lot about time expenditure, but are there any other software limitations?
Not really. It's just you have a huge number of floating point operations that need to be done whenever you have particles in 3 dimensions, and when you have electron and a positron and then have separate centers, all of that gets multiplied up, and you just end up with having multi-parameter systems, and you have to check for convergence in all of your expansions and all of those very complicated things. It's just that the problem is so exceptionally difficult.
Well, I'll throw back to the audience then. Do we have any more questions for Igor?
There's one at the back. All of them, yes. Yes. So in quantum mechanics, all of the fundamental aspect of quantum mechanics is that it's probabilistic. So all of those collisions have a probability of happening, and some are much higher than others. So elastic scattering is far more probable than positronium formation. And so in our calculations, we actually calculate probabilities. And the people want to know what is the highest probability for generating anti-hydrogen, and that's what we provide. Because all of those other processes, in fact the paper that we're writing right now for physical review letters is the first complete calculation that has not only anti-hydrogen formation, but it also has the breakup of positronium, and also has positronium formed in high excited states. So all of the possible outcomes are calculated because it actually affects the experimental approach to the problem.
Well, we'll end the questions there because we're reaching the 20-minute mark. But Igor will be back for the panel at the end if you have any more theoretical physics questions. So our next presenter is the head of the Epoch of Reionization group at Kyra. And presenting on that very topic is Associate Professor Catherine Trott.
All right, good afternoon, everyone. Thank you for coming. It's nice to have a nice big audience, and thank you for inviting me to talk about some of my research. So I'll touch a little bit on some of the discussion that Melanie had with the Murchison Wide Field Array, but with a very different application. And I'll also talk a little bit about the Square Kilometre Array. Okay, so astronomy at the cosmic dawn, searching for the first stars. So the epoch of reionization is a period in the very early universe when we have the formation of the very first generations of stars in the universe. And it's a very important epoch because at the moment we haven't observed it, but it fundamentally changes what the universe looks like. And so it's an era that we are trying to explore. And a lot of the work we're doing here in Western Australia is with the Murchison Wide Field Array. And so Melanie showed you one of these tiles of the MWA, but actually there's 256 of them in the desert. And I'll get into that in a little bit, but this is some of them. Okay, so just to place in context some of the telescopes that we use in Australian astronomy at the moment in the optical and in the radio, and also some of the international telescopes that we're working more and more towards. And in astronomy, bigger telescopes means you can collect more photons, you're more sensitive, and in general that means that you can do more challenging science and answer bigger questions, a little bit like what Igor was talking about with having bigger computers and able to solve the problems that we couldn't solve 10 years ago, 20 years ago, 50 years ago. So this is a very logarithmic scale of the universe as we go out from our own solar system into the local stars, the brightest stars, the ones that we can see in our night sky, just going outside and then moving out of our own galaxy into the local groups of galaxies. And as we go out further into the universe, we can see the clusters of galaxies, that cosmic web that Melanie was talking about that she'd like to detect. And beyond that, we get to the point where we no longer have galaxies anymore because they haven't formed, and we're getting into the very early universe. And so we're looking more than 13 billion years into our past at this point. The first billion years of the universe, that's when the first stars and galaxies form and transform to a universe that looks very much like the one that we see around it today. At the end here, at the right-hand side, we're at the sort of the limits of the Big Bang, and those first few 100,000 years of the universe where the photons and the baryons were tightly coupled together in a sort of a big fluid, a big soup that sloshes backwards and forward. And it's that sloshing that creates that characteristic scale of the cosmic web. And at the cosmic microwave background, that's about 400,000 years after the Big Bang, that's the point at which the universe has expanded enough that the photons and the matter decouple. The photons travel off into the universe in what we call now the cosmic microwave background because it peaks in the microwave part of the spectrum. And all of that matter is left behind. That matter goes on to form the stars and galaxies and forms all of us. We would like to know where that comes from. But if you're interested in understanding that characteristic scale of the universe, do the 4th year Advanced Topics in Astrophysics course and you'll learn all about it. Okay, so Melanie talked a little bit about why we do radio astronomy. Optical astronomy is something that everybody is very familiar with. The images look like what we see with our own eyes, but of course we have a much broader electromagnetic spectrum, and by looking at different parts of the electromagnetic spectrum, we're looking at different energetics, different energy levels in our astrophysical sources, and that can tell us different things. And when we put information together from a range of wavelengths, we're often probing very different physics that's happening within the same source, and that helps us understand what's actually going on. So why do we do radio astronomy? Radio light is a much lower energy than optical light, but there's a few really characteristic astrophysical processes that give us radio emission. So first is sort of broadband emission, so something over a very wide bandwidth. So synchrotron emission is one of these. Melanie talked about that. There are a lot of magnetic fields in the universe. Some of them are strong, some of them are weak. But when you have when you have a plasma, when you have charged particles, they spiral around magnetic fields and you get broadband synchrotron emission. And so a lot of the studies that we do look at synchrotron emission, and that's where we have black holes, that's where we have star-forming galaxies, and these are all the points that you saw in Melanie's images. There's also thermal emission, so objects that are relatively cool, they might have the peak of their emission in the radio, and so that's another case where we see a lot of radio emission from cooler sources. There's also a lot of spectral lines that emit in the radio, and one of the key ones is hydrogen. So hydrogen has a hyperfine line, that's a nuclear emission line, where the presence of the electron either in the spin up or the spin down state means that there's a slight energy difference in the proton for that bound hydrogen atom. And that is emitted at 1.4 gigahertz, which is in the radio. And hydrogen being the most ubiquitous element in the universe, it means that this is a really key emission line that we can look for to show us where hydrogen is, and therefore to map a lot of the evolution of the universe. So here's just some diagrams of different things. So this is actually possibly one Melanie even showed with supermassive black holes, star-forming galaxies, cool stars. So this is cool in a temperature sense, not in that they're really cool. These emit thermally at radio wavelengths. Pulsars, or rotating neutron stars, we also observe in the radio. But what I'm interested in is the hydrogen gas. And this is because very early in the universe, when we have that decoupling of the photons and of the matter that's left behind is mostly hydrogen. It's about 75% hydrogen, 25% helium. So at this point, the universe is full of a fog of neutral hydrogen atoms, and they're all emitting this emission line. And so if we can study how that emission line changes over space and over time, then we get an understanding of the evolution of the universe. And so this is the signal that we're interested in looking for. If I can get it to move on. Oh, there we are. Is that one forward? Yes, it would have been. Okay, so this is another view of the full history of the universe. So time is moving forward towards the bottom of the screen here. Here we have this very even soup of plasma and photons that are coupled together. And this period here we call the cosmic dark ages, and that's because the light from the cosmic microwave background is just free streaming in the universe. We don't have stars and galaxies yet, we just have dark matter, we have hydrogen, we have helium, but otherwise we have no light. This period we can try to study through that hydrogen emission line, because hydrogen is actually emitting at that emission line. But other than that, we don't have any other sources of light that we can see. And so this is why it's called the cosmic dark ages. But as those baryons coalesce onto those first seeds of dark matter halos and start to compress together under gravity and release energy until they're tightly coupled together, and you get thermonuclear ignition, you have the very first stars forming in the universe. And at that point, and this is a nice artist's impression of this is a bit hard to see with the lighting, but what you have is this fog of gas, and as you move forward in time, those first stars form, thank you, and the ionising radiation from those stars eats away at that hydrogen. So it rips the proton from the electron, and your signal goes away because you no longer have that hyperfine transition because the electron needs to be present in the atom for that to happen. And you get these ionised bubbles around these very first sources of light. So now what we can see is that we have structure in that hydrogen emission line, and the structure follows where the first stars have formed. As we move forward into the universe, we go through what's called the epoch of reionisation, and now you can see why it's called that. You're reionising all of that hydrogen gas to get to a universe where we live at the moment, where there's no hydrogen gas in its neutral form just floating between the galaxies. There's only hydrogen actually just shielded within galaxies themselves. And so you go from a universe that is this opaque fog of neutral hydrogen gas and is otherwise dark, to one where you have the very first stars and galaxies and you have all of that hydrogen being ionised away. So it's a major phase transition in the universe, and it all happens within the first billion years. Oh, it's there. Thank you. Oh. I just have... Thank you. So this is another way of looking at this. We're now moving forward in time from the Big Bang. You can see the time at the top here, 10 million, 100 million years up to a billion years. And one way that we can actually try and study this at this period of the universe is to look at the temperature of the gas. And this is not its kinetic temperature, it's not its motion temperature. It's actually the observed brightness temperature. And so it can be cooler than the microwave background, and so we see an absorption, which is what this period is here, or it can be in emission, it can be hotter than the microwave background, which is sort of our contrasting light in the universe, and this is where it's actually hotter and therefore it's an emission. And if we could make slices through the universe and look at what this looks like, you can see that the temperature changes over time and also the structure changes over time as those first stars and galaxies form and eat away the hydrogen gas around them in these ionised bubbles. And so we like to measure this temperature as a function of time to try to explore this epoch. And you can see the brightness here. At its peak, it's about 100 millikelvin. And this is in a universe where at these frequencies, the universe is about 2000 Kelvin. So you need a very high dynamic range to pull this signal out from everything else in the universe. All right, so we have a movie now. Will this start the movie? No. Could you just start the movie on the left, please? So this movie is a simulation, just on the left, thank you. This is a simulation of what that temperature looks like in sort of a cubic area of the universe. And what you can see is different colours, and you can see different structures as we move forward in time. And this is what we would see if we could map the structure of that hydrogen gas as a function of time. And we get to this point at the end here when most of the hydrogen gas has been torn apart and our signal goes away. And so this is what we'd like to observe with our radio telescopes. But it's exceptionally difficult. And if we can observe that, then this gives us clues to a lot of the interesting astrophysics in the early universe that we currently don't know much about. The structure of the first stars, how massive they were, how bright they were, how long they lived, how clumped together they were, what were the conditions in the gas in the universe at that point. These are all unknown problems that we'd like to be able to solve, and that's because our temperature fluctuation is a combination of all of these different physical effects that encode the density of the matter, how much is ionised, what the radiation field looks like from the first stars, and also the underlying kinetic temperature of that gas. So there's a lot of telescopes around the world who are looking for this signal. The ones that are operational at the moment are the MWA here in Western Australia, LOFAR, that Melanie talked about in the Netherlands, and looking to the future, we'll be using the Square Kilometre Array. So here is where the MWA lies. It's in the Murchison region of Western Australia. We go out there because the frequencies we're interested in looking at overlap with FM radio frequencies, as well as a lot of other radio frequency interference. And so we need to get away from people, we need to get away from towns, anything that's going to cause that interference. And here for scale is one of our researchers, Nicole Barry. She's from the University of Melbourne, sitting in one of these tiles. And so we use these dipoles to measure the signal, because this is something that has a wavelength of 1 to 2 metres, so very long wavelength radio waves. And so this is a little bit like a TV antenna. So the MWA does a whole range of science. This is only one of the science cases. You can see that Torrance's jellyfish has appeared here as well. Here is Gleam again, looking at our own galaxy and other radio galaxies. We can look at the structure of pulsars. We can look at these radio galaxies. Again, Melanie showed this before. And we can also look at the structure of the ionosphere. As Melanie mentioned, this refracts and scintillates our radio waves, and so we can use that to actually study our own ionosphere. And looking to the future, we'll be scaling up from the MWA, which has 256 of these station tiles, to the MWA, to the SKA. It will have 512 stations, each of which has 256 of these dipoles. So that's 131,000 dipoles spread over 65 kilometres in the desert. This gives us very high resolution images, very sensitive, very detailed. And with that, we want to take the next step in the science. As Melanie said, we need to have the computing come along with that, but that next step in the science will allow us to go from detecting signals from the epoch of reionisation to actually really exploring and mapping and imaging that period. So we can actually image those bubbles around the first stars. It's a very, very weak signal, so we need a lot of sensitivity to do that. The SKA is an international project. We're very lucky that Western Australia is very empty, and therefore the low frequency array will be located here. It means that in your lifetime as researchers, if you want to do astronomy here in Western Australia, then SKA is an excellent place to do your research. There's a lot of different challenging science questions that we'd like to be able to address with the square kilometre array. Because it will be so sensitive and so high resolution, we'll be able to answer a lot of the questions that we haven't been able to answer before. Looking at strong tests of gravity, working with black holes that James will talk about, cosmic magnetism. The cosmic dawn is the one that I'm interested in. But there's also the cradle of life and all the things that we haven't thought of yet because we've never had an instrument or a telescope that's been big enough. So, radio astronomy in Western Australia, on the path to the world's largest telescope, the Square Kilometre Array, we'll be finding evidence of the very first stars in the universe, 13.5 billion years in our past. We'll be studying black holes in great detail, and James will talk to this a little bit. Strong tests of general relativity, using pulsars spread across the universe as clocks to see space, this fabric of space-time change. Measuring the shape of the universe, so large-scale cosmology, and also all of the undiscovered, unthought-of questions that will discover new things in our data just because we've never been able to look at the universe in such detail before. And I'll finish there. Thanks.
So you cut it really, really close. Yeah, I probably would have cut you off in about 15 seconds from there, but... So I'm going to switch the lights back on. But do we have any questions for Catherine? On the epoch of reionisation, on Murchison-Whitefield array? Callan?
We've never observed it before, so from that point of view, it's an unknown. But we expect that the first stars were very different to our current generation of stars, because our current generation of stars is made from a range of elements. But the first generation of stars only had hydrogen and helium, and so the hydrostatic pressure is very different. So we expect them to be very massive, tens to hundreds of solar masses, and to die very, very quickly within 1 million or 2 years. In terms of the clustering together, I think it really depends on your model as to how that looks. But we do expect that first generation of stars to be fundamentally different to the current generations.
Do we have any more questions?
Yeah, that's a really good question. And this will be on for the SKA as well. In general, because there's no moving parts, they're just dipoles that sit on the ground, they actually weather very well. The largest problems we have some problems with lightning. So if lightning hits the receivers, that can knock them out. But most of the problem we have is with animals coming and chewing on cables, rubbing themselves against the dipoles. So we've had big animals come through and rub themselves against the dipoles and move things. Other than that, the maintenance is fairly minimal. It's built to withstand the Australian desert, and so it has to be fairly robust.
We've got a question over here.
That's a great question. If we were, so the MWA operates between 80 and 300 megahertz, but some of the science we want to do is at higher frequency, and so the antenna is actually different because it needs to be broadband. It needs to go from 300 up to about 600 megahertz. So the MWA antennas are about this big. They're little spiders on the ground. The current SKA antenna is 1.8 metres tall, and it looks like a Christmas tree, and that's because at the top end you get the high frequencies, the bottom end you get the lowest frequencies. So it's fundamentally different. It's very, very big, and you have to design it to not have a lot of wind load, so it doesn't move around. Other than that, it's fairly similar. It's a piece of metal that has arms that are of a half wavelength long.
We can probably fit in just one more question here, if anyone has one. Okay, well, if anyone comes up with a question, Melanie, you're not Melanie, you're Catherine. Catherine will still be here for the panel at the end. So let's thank Catherine again. So now from the beginning of the universe, we're moving on to some of the most catastrophic things in the universe. Black holes, which, I mean, you don't really need any more introduction than that. Presented by Professor James Miller-Jones.
All right, thanks very much for having me. It's great to talk about something that fascinates me, and one of those topics in physics that's entered the common lexicon. So I'm going to talk about black holes. Again, I want to try and put these lights down. Where was the... this one. All right, perfect. So we all think of black holes as big cosmic vacuum cleaners, effectively. What I want to talk to you about is how they actually, they're not just vacuum cleaners, they're engines. So they generate energy in very, very small regions of space, something just a few kilometers across in the case of a stellar mass black hole, or maybe something that's about the size of the solar system in the case of a very massive black hole, such as the one that was recently imaged, and pump that energy out to vastly greater scales. So in the case of M87 over here, to scales of hundreds of thousands of light years. So I imagine that many of you have seen this image in the press. It made the front pages of pretty much every newspaper in the world when it first came out a year or two ago. And so this is the first image of a black hole. So what we have in the center, that's where the black hole lies. That's not actually the event horizon. This is something about 5 times the size of the event horizon, and what we're seeing is the shadow. So within that region, photons can't actually make it out. So we think of a black hole in terms of its escape velocity. So here are a bunch of well-known astrophysical objects. We have the Earth up here. The escape velocity is about 11 kilometers a second. So if we're sitting on the surface of the Earth and we want to launch something out into space away from the Earth's gravity, we've got to fire it outwards at 11 kilometers a second. As we make objects more massive and more compact, that escape velocity goes up. All right, so it goes as v squared is proportional to m over r. So for Jupiter, it's about 60 kilometers a second. For the Sun, it's about 600. For a white dwarf star, so this is something with about the mass of the Sun and the size of the Earth, that's up to a few thousand kilometers a second. For neutron stars, the most dense form of matter that we know of, basically a star-sized piece of atomic nucleus, the size of a small city, if you like, a few kilometers across, with a solar mass inside. Escape velocity is about half the speed of light. And then if you make something even denser than a neutron star, such that not even light can escape if you try and shine it outwards, that is a black hole. So the escape velocity is defined to be the speed of light at the event horizon. Now, if you are not firing the light directly outwards, but it's actually moving with some trajectory that skims the black hole, if you like, then you have to be a bit further away before it can escape to infinity, and that's why the image that was made by the Event Horizon Telescope Consortium over here, this is a few times the size of the event horizon itself. All right, so black holes are actually very, very simple objects, so we can characterize them purely by 3 quantities. So they have a mass, they have a charge, and they have a spin. And this is known as the no-hair theorem. So a black hole astrophysically sized, it should not be charged, because otherwise it will pick up the opposite charge and become neutral again. So we can parameterize an astrophysical black hole by just its mass, which we can measure, and its spin, which we can actually also measure. Okay, so this is a movie made by the Event Horizon Telescope Consortium that zooms in on the black hole that they imaged. So this is a black hole in the center of the nearby galaxy Virgo A, M87, and it's about 6.5 billion times the mass of the Sun, and the event horizon is roughly solar system sized. So can you play that? Or can I play that? Oops, sorry, try again. Yeah, there we go. So we're going to zoom in from the, this is the ALMA telescope in Chile. So we're going to zoom in on the galaxy itself. So this is we can see the galaxy itself in the optical band, but the observations with which they actually imaged it were made at sub-millimeter frequencies. So what I want you to see as we zoom in, you can see this big radio emitting structure around it, a few 100,000 light years in size, and that's powered by the jet, this curious straight ray that's coming out from the black hole itself, launched very, very close to the event horizon. So this is a composite of real images made with very different telescopes from the optical through the radio band until they reveal the shadow of the black hole. Okay. So what I want to focus on now is what those jets do. So how these black holes actually pump energy out from very close to the event horizon out to these very, very large scales, hundreds of thousands of light years, to inflate those enormous structures that we saw as we zoomed in, and the ones similar to what Melanie showed you before. Okay. So here we go. We have a black hole. As stuff falls in, it releases a lot of energy. It's very, very efficient at releasing energy. So in theory, if I drop something into a rapidly spinning black hole, I can liberate 42% of its rest mass energy. Now we compare that to what we get from nuclear fusion, which powers all the stars in the universe, the things that we actually see when we look up into space. The efficiency of that process is about 0.7%. This is the best way we know of extracting energy from mass. Okay? That energy we see as radiation, so we can see it from the material that's swirling around the black hole. That's the sort of whirlpool-like structure that we have here. That's gas that's flowing around as it falls inwards. It heats up, and heats up so much that it can emit even the X-ray band from the very central regions. As the gas swirls around, it twists around the magnetic fields that are embedded in the gas, and that allows it to power these jets, so these collimated beams of matter and radiation that can be launched from the inner regions. Now, we don't know exactly how they're launched. There's a few different theories, but they all involve twisting these magnetic field lines around as the material swirls around the black hole itself. And it's these jets that are responsible for carrying energy away from very, very small scales, so in M87, from scales about the size of the solar system to scales of hundreds of thousands of light years, to inflate these enormous bubbles in the surrounding gas. So here we have this image that I think Kath already showed. So we have the galaxy Hercules A here at the center. It looks like just a normal galaxy if we look in optical light, whereas if we switch around and we look with radio waves, a radio telescope can actually see the big bubbles that are inflated by these jets flowing out from the supermassive black hole at the center. What it's seeing is the synchrotron radiation from electrons spiraling around the magnetic field lines that are being carried away by the jets from these tiny scales to the larger scales. And we want to understand, how does that process happen? It's responsible for excavating these enormous structures, displacing vast quantities of gas from the intracluster medium. So these are really significant processes on the scale of the universe itself, and we want to understand more about them. How do these jets work? How are they launched? How do they transport energy outwards, and what does that do to the surroundings? So while there are many, many of these supermassive black holes, millions to billions of times the size of the sun, and those are the ones that have the biggest effect on their surroundings, they actually evolve very, very slowly. So the bigger a black hole is, the more slowly it evolves. So if we want to actually see these things change in real time, we need to look at smaller black holes. Now, happily, there are many of those floating around our own galaxy. Estimates go up to maybe something like 100 million black holes floating around the Milky Way galaxy. We can only see them when they're actually feeding on gas, so they're feeding on material from another star, typically in orbit with the black hole, and that provides a steady source of gas for the black hole to feed on. And we can look at how the material flows in this swirling disk of matter around the black hole, and we can see that in the X-rays, and we can see how it varies over time, and we can see how those changes result in the ejection of these very, very powerful jets, and try and figure out how that process occurs, and what's the physics underlying this really important feedback mechanism. Okay. So here we have, once again, M87. So here's the black hole imaged for the first time by the Event Horizon Telescope Consortium. So this is a tiny, tiny angle on the sky that they measured. The resolution is 42 microarcseconds. So an arcsecond is 1/3600th of 1 degree. So this is 40 millionths of an arcsecond, which is about 10 times the size of the Event Horizon in that case. So here is that larger scale jet that's flowing out of the black hole, seen at lower resolution with a different telescope, at slightly lower frequency. And we can image that very, very well. Now, in these smaller black holes in our own galaxy, we can see similar jets. So here's one example in the black hole Cygnus X1. This was the first black hole ever discovered. The thing is, the black hole there is maybe 1 billion times less massive than the one here, but it's only about 10,000 times closer to us. So we don't have a hope of actually seeing its event horizon. But what we can do, because the black hole is so much smaller, we can watch as it evolves in real time. So rather than evolving on timescales of years, decades, and centuries, these things actually evolve on timescales of milliseconds, hours, days. Right, so we can watch them change, and that means we can watch how the jets form and how they evolve. How do changes in the inflowing gas lead to these very, very powerful outflows that drive these enormous structures in our universe and help to shape it? Okay, so what we think happens, could we play this movie, please? So here we have a black hole that's accreting matter from a normal star. It's an artist's impression of what happens here. So we have mass flowing from the normal star into the gravitational potential well of the black hole. It swirls around in this accretion disk because it carries angular momentum. And sometimes an instability in the disk takes hold. Matter flows into the black hole very quickly, releases a lot of energy, and some of that energy comes out in the form of these jets. And we can watch those form on timescales of days or maybe even minutes. Okay? So the next thing I'm going to show you is another animation. So this is based on real data. Taken with multiple telescopes based across the United States over a 4-hour period. And over this period of time, we can see these jets actually forming and evolving and moving away from the black hole. So here we have the radio emission from the very center of the system down close to the black hole. This is time, and this is the size scale relative to the solar system. And you can see these jets forming and moving out in real time, which allows us to track how and when and why they're formed. Okay, so this was some work that we did a couple of years ago. And what we can do with that is we can track each of those jet ejection events. So we can see the jets are moving with respect to time. So this is our 4-hour period here. And we see something like a dozen individual jet knots being ejected. You can see they're being ejected at different angles. So this is as seen on the sky. You can see that they're tracing out this cone-like structure. And what we think that is a manifestation of general relativistic precession close to the black hole. So here's an animation of what we think is actually going on as that process occurs. So we have the black hole. It's in an orbit with a star maybe 0.7 times the mass of the sun. It's ejecting these knots of plasma that emit radio waves. What we think is happening is that the spin of the black hole's rotating. And that spin is not well aligned with the plane of the orbit. And so material that's out of the orbital plane of the black hole is forced to precess according to general relativity. And as the material falls in at a very, very high rate, radiation pressure puffs up the inner regions into this donut-shaped thing, this torus, and that precesses about the black hole spin axis, like a spinning top. And so as the material gets ejected, it's forced to move in the same direction as the torus. The magnetic fields and the pressure of the torus dictate the directions of the jets. So the black hole is spinning around, space-time is forced to, it's dragged around by the spin of the black hole, and that's what causes this precession. So what we really want to do is then tie back the ejection events that we're seeing in the radio band with signatures of the inflow in the X-ray band to tell us, okay, how does that inflow of material in towards a black hole couple to the generation of these very powerful jets that drive these powerful outflows and blow these enormous bubbles in the surrounding gas, affecting star formation in their host galaxies, affecting the evolution of the entire galaxies and the galaxy clusters in which they reside. So that's the basic questions that we're trying to answer here. So moving forward, we can make these images, we can take these data, but a big challenge now is trying to get the most out of those data. So as I've said, as I showed you, we can make a movie from each individual frame, 2 minutes of data. The trouble is, it's evolving over time, and the way a radio telescope works is that as the Earth rotates, the distance between the two telescopes, as seen from the source that we're looking at, it varies. So the Earth spins around, and the projected baseline changes over time, and that allows us to sample different pieces of information. It's actually a Fourier transform relationship between what we measure and what we see on the sky. And so to try and reconstruct that, we need as much information as possible to reconstruct it accurately. At the moment, with just pure snapshot imaging, we can only get the very minimum of information out of each individual couple of minutes of data that we have here. But there are more sophisticated techniques being explored by the likes of the Event Horizon Telescope Consortium to deal with rapidly varying black holes, such as the one at the center of our own galaxy, Sagittarius A star. And we're working with them to try to apply those same techniques to these smaller black holes that are changing very fast in real time, to get as much information out as possible about the jets from these systems, and to be able to couple them as best we can to the information that we get from the X-rays about gas flowing in towards the black hole. So I think that's pretty much what I wanted to say. This is just an overview of some of the exciting research that we're doing over at Kyra in this field. Here's a few credits for the images that I've used. So happy to take any questions. Thank you.
So I've got to say, you have a very high special effects budget. So it's black hole presentation, and usually you'd expect a lot of questions on that, so probably the same today. So let's begin. Any questions on black holes for James? Up the front here.
Okay, so you would start off with a binary system. Most stars are born in binaries, so they're born as pairs or maybe even multiplets, so triple systems, quadruple systems, etc. So maybe 2/3 of stars, I think, are born in binaries is roughly the current estimate. And what happens is as they age, those stars evolve. So a star spends its entire lifetime burning nuclear fuel in its center to provide the energy to prop itself up against gravity, trying to pull it together. When it runs out of fuel, gravity takes over and it collapses. The more massive the star is, the faster it has to burn its fuel. So a very massive star that might end up as a black hole will live just a few million years, whereas a low mass star like the Sun is going to live for about 10 billion years. So what might happen is you're born, you have a system that forms with one fairly massive star and one less massive star. The more massive one evolves faster, turns into a black hole. And the less massive one is still something just a bit like the Sun. However, as it starts to run out of fuel, it will expand. And as it expands, its surface gets closer to the black hole. And at some point, the force inwards towards the center of the star is less than the force in towards the center of the black hole. And so some of the mass on the surface can then get transferred into the gravitational potential well of the black hole and start falling in towards it. And those systems, they can last for a few billion years even, as you're not
destroying the star. It's just a gradual flow of matter from the outside parts of it in towards the black hole. It will actually reduce the lifespan of the star because you're stripping gas away from it, so the star becomes less massive. It actually affects the stellar structure in the interior as well. And then you have other effects such as the radiation from the black hole, the gas falling into the black hole impacts on the star, it's dumping energy into it, and there's all sorts of complicated effects that are going on in that sort of binary interaction that you can simulate. So there's, trying to figure out how binary systems evolve is a lot more complex than just having single stars on their own, just because of the way gas flows from one star to the way that the radiation from one star impacts the other one, etc., etc.
I'd like to throw in my own question here. Is there any relationship between accretion disks and just orbiting material?
Yes, so an accretion disk is a way of transferring angular momentum. So the Earth is not falling in towards the Sun. The Earth is stable, it's been there for about 4.5 billion years, and it's not fallen in towards the Sun yet. It conserves its angular momentum. So angular momentum is conserved, that's a principle of physics. So if I have gas that's in an orbit around the black hole, and I want it to move inwards, it has to lose angular momentum. So how does it do that? It has to transfer it to other stuff, which can then move outwards. So overall, angular momentum is conserved. And an accretion disk is a mechanism for transferring angular momentum. Basically, viscosity, so material in one orbit rubbing against material in a slightly smaller or a slightly bigger orbit, that transfers angular momentum and allows some material to fall in, lighting up and allowing us to see it. In the meantime, other material is moving away to larger distances. Okay.
So I'll throw back to the audience now. Any more questions? A question up here.
So a supernova will have an impact on the star, that's certainly true. Yes, a couple of things. You can actually form a black hole by direct collapse. If it's massive enough, it can collapse directly into a black hole without a supernova. But we think that a lot of them do in fact form in supernovae. A star is more tightly bound than a planet. Right? You have to put a lot more energy into a star to break it apart than you do a planet. It's just more massive, and gravity holds it together more tightly. So for that reason, a star can survive a supernova remnant in a way that a planet might not. So whether or not a planet orbiting the other star would survive, I don't know. I'm not actually sure if I've seen any calculations about that. But certainly, yes, I mean, these stars do tend to survive. Now, it's possible that you can actually disrupt the binary system, because during that supernova, you get a kick, which can, if there's an asymmetry in the supernova, it can actually unbind the binary system completely, and then the black hole would escape. And we would never see it because there's no gas falling in to light it up. But yes, we think that we know of probably several dozen binary systems like this in our own galaxy. And so there's clearly a significant number that are able to survive these sorts of explosions.
So we'll end James's question time here, but our panel is coming up in about 2 minutes. So you can still ask more questions if you have them. So our presenters would have noticed that I let many of them go over the time limit that I mentioned to them. That's because our final presenter, Liam Scarlett, was unfortunately unable to make it today due to personal reasons. So we will move straight on to the panel, which will involve 3 of our presenters and also a third-year undergraduate student, Jordan Hoffman. So our presenters, Professor Igor Bray, Associate Professor Catherine Trott, and Professor James Miller-Jones will be returning. Yeah, just a seat. Yep.
All right, hi guys, just before we start, just to give a bit of an introduction of myself again. So I'm a third year student, as we said, and I'm kind of here just to answer any questions on student experience. I did a project with Igor in first year on what he presented today, did a project with James over the summer on what he also presented today, and I'm now doing a project with Alicia, which is one of Igor's colleagues on something similar on collision theory. So if you have any questions about any of that, yeah, feel free to ask now.
So we can start with questions for the panel whenever we like. They have 2 microphones, so we'll start over here.
I have a question which I guess is kind of open, but probably most to like advanced work. The image of the black hole by the Event Horizon Telescope obviously made massive national news, international news. I'm just wondering if there were any takeaways in terms of the actual academic community about physics of general relativity, or was it mainly just the public interest scientific achievements?
No, I mean, that absolutely had huge scientific impact. So I think there were 6 papers that were all released at once at the time that the image was released, exploring both how they did it, which was a huge technical achievement in and of itself, but also what it tells us, the astrophysics that it tells us. So it told us, allowed us to refine how massive the black hole was. It allowed us to show the black hole was spinning, in which direction the spin was occurring, by comparison with theoretical models and simulations. It allowed us to say something about how the jets were actually formed in that black hole. Gave us all sorts of physical parameters of the system, the gas temperature, the accretion rates, etc. And something Igor can probably talk to as well. It did in fact help test general relativity in terms of the predictions of what the shadow of the black hole should look like were verified. Maybe Igor wants to say some more.
Very kind segue here, because that picture is straight out of my PhD. And I had this idea that if you wanted to detect a black hole, you needed to use its effect on background radiation, and specifically its spin, to create an axial asymmetry in the image, which would identify the source as a black hole. And I couldn't believe it, that almost about 35 years after publication of my paper, this came out, and it was entirely consistent with the pictures that I had in my published paper in Physical Review D. And it showed that if you have spin for a black hole that's near its maximum, that's allowable by general relativity, then you will see a substantial deviation from a perfect circle. So when James put up that picture, you could see that the black part was not a perfect circle, it was much more elongated, and it was postulated that is solely due to the spin, not solely, but considerable contribution due to the spin of black hole. So yes, so for me personally it was a fantastic thing, particularly since my paper received absolutely no citations after it was published for 13 years. And in the last 2 years it's got more citations than in any of the previous years.
Well, let's go back to the audience. Are there any more questions? Up the front here.
I mean, I certainly think it's always great when there's some media about astronomy, about science. I think it can help to inspire people, even if it just raises a bit of, oh, that's interesting. I think it's really good. Now, yes, they've given rise to a whole genre of sci-fi. Are they wormholes, et cetera, et cetera. And in a way that drives engagement, I think is great. So it doesn't ever annoy me. Now, obviously, there are, as scientists, we always have, we tend to caveat what we're saying because we want to be very precise about what we mean and what we do not. And so I would always qualify things a lot more than maybe the typical coverage of a black hole. I mean, I have a collection of fantastic headlines from black hole related articles in the media that amuse me, but by and large I think it's always really great in that it can stimulate interest and inspire people to learn more, and anything that does that is a good thing.
Certainly that's quite relevant to the Curiosity Showcase as a whole, as being an event intended to stimulate interest in various fields within physics. And we'll throw to Callan.
I've got a good question for everyone about the evolution of international collaboration in science. So obviously with things like the SKA, with the PhD collaboration, with things like fusion research globally, with that, all of those evolving, what are some of the, I suppose, biggest problems or biggest difficulties facing the evolution of international collaboration?
I think that's a good question. I mean, international collaboration has certainly been enabled a lot more easily over the last few years because of Zoom calls and Slack and a lot of just the ability to directly contact people. One of the challenges is just time zones, actually being able to get people together in a time when everyone's brains are working. It means for researchers, it's that can be just challenging from a personal point of view. I think that we are getting a lot better at having international collaborations that are quite culturally diverse as well. In the past, I think there were a lot of collaborations between English-speaking countries, and it was often more difficult in countries where the science was not as well, like that your actual research field might not have been as prominent, but it's become much easier now in some of these large international collaborations for a lot of prominence from a lot of different countries to come to the fore. And so we regularly now have telecons with people from 10, 20 different countries that are geographically distributed around the world. It does mean that the language of science is English, so we have an advantage, and in other countries that's a challenge. But that's something that we can work with as native English speakers to ensure that the communication is really strong so that people don't get left behind because they're actually communicating in a language that's not their native language. And I think with international travel is not happening much at the moment, but in general, international travel and the ability for people to travel from country to country and collaborate that way, which is much more open now, really helps with that and enables it more.
As a follow-up to that question, so there's been an increase in international collaboration. Has there been much of an increase in recent decades in interdisciplinary collaboration?
In some places, yes. In some places, there's actually been a large increase, and there are communities that work very well together. In radio astronomy, the engineering community and the astronomy community now work very closely, and because it's sort of demanded by the challenges of the telescope. Interdisciplinary research in general has always been a challenge, and here even at the university it's something that we work towards within the school, to have the disciplines work with each other, because we do find that when we do that you move forward and it's quite advantageous, but often even just different disciplines use very different language, and so there's often just a language barrier from a jargon point of view that needs to be overcome. I think it is definitely getting better, but I think we still have a long way to go, and there's a lot of people thinking about how we can ensure that we can have truly interdisciplinary research. Someone else might want to add to that as people who've thought about it.
So science has always been very international, collaborative, but it had issues associated with communication, travel. When there was the Iron Curtain, even then Soviet scientists would be highly valued and invited overseas. So it's inherent in being a scientist. We are all global citizens. With the communication as it is now, it's just phenomenal. I mean, very few of us would now physically go to a library, right? And I get collaborations because Google sent me a notification. Somebody cited my article. I read that article, find out they actually weren't up to date. I contact them, and we end up writing papers together. And the multidisciplinary connectivity is really enabled by that communication. First of all, as Kath just said, starting to speak the same language. People do have their own community, so that's because of our capacity to talk to each other so much more these days. It really does enable multidisciplinary activities where people utilize. It can be in parallel and it can be sort of more vertical. So we calculate things at a very fundamental level, but the outcomes of our calculations are then used in vastly different applications. And we need to know what people need. And when they get that communication going, then things really start to happen. And the other thing I should add is, in my experience, not being in the center of where a lot of the action is can be very advantageous. The reason being is that to get things done, you need time and peace to concentrate and not travel quite so much, because traveling is actually very disruptive on many different levels. So oddly enough, I have found that being some distance away from not going to conferences quite as much as my colleagues would be in the United States or within Europe has been to my advantage, because I could settle down, actually deal with the problems and advance things because of not being too busy communicating. So you have to find the right balance. And lastly, just to say what is normal these days. So in my case, I have a collaboration that involves Europeans and the US colleagues, and we meet fortnightly via Zoom at 9 p.m. my time, so that we can catch the early morning in the US and the afternoon of the Europeans. And this is normal. This is the way things can be done now. We meet via essentially like Zoom, not quite, it has to be something more secure for my NIST colleagues, but this is the normal day of a scientist today. It is very global from the outset.
Well, that's probably going to make a very interesting standalone YouTube video. But we will throw back to the audience for now. We've got another question over here.
I mean, certainly, so CAIRA, the Curtin Institute of Radio Astronomy, was set up deliberately as a multidisciplinary team to bring engineers and scientists together so that the scientists could say what they wanted to do and the engineers could tell them what was possible. And that could be a very mutually beneficial relationship and very, very powerful. And there are only a limited number of other institutes in the world with that multidisciplinary ethos, bringing together the scientists and the engineers to further, at least in astronomy, to further what can be achieved. Obviously, supercomputing has been a big part of radio astronomy, as Melanie has said. And so the beautiful thing about having all these different experts in one building is that nobody needs to be an expert on absolutely everything. You can draw on the strengths of a very wide range of different people with different skill sets to solve a problem. And this goes back to the the international and multidisciplinary collaborations that we've just been talking about. I would also say it's not just opportunities within Cairo or within ICRA in the engineering or computing spaces, but also externally with industry partners, for instance. I know Kath has had a lot of success. Maybe she wants to say a bit more about that.
Yeah, sure. So some of the data that we got from the MWA, there was a paper we wrote last year where we processed 4 years of data. It was about 800 hours of observations in total, and so it was a very, very large amount of data. And we didn't have the compute to process all of that. So we partnered with a company here in West Perth, down under Geosolutions, who work with geophysicists and geophysical data. And they have a very green supercomputer in West Perth. It doesn't use very much power. And they were able to help adapt the algorithms to be able to process the data. And they processed it incredibly efficiently and sent it back to us. But that required, I didn't have to be an expert in HPC, and they didn't have to be an expert in my science, but we needed to have a few meetings to talk through what it was I was trying to do and answer questions. And you said, how much do you need to be an expert in all these different things? You don't. You need to have your domain knowledge, and then it's about speaking to someone over a lunch table or knocking on their door, which at Cairo we have the advantage to do because we're in the same building, and saying, this is what I want to do. How is it possible? And the engineers might say, we've got this great antenna, it's got this weird resonance at 100 megahertz, but otherwise it's beautiful. What science can you do with it? And we'd say, well, that's exactly where my signal is, so that's no good. You don't need to be across everything, but you can do anything from antenna design, signal processing, all the way through to theoretical astrophysics, and we have people across that whole spectrum. We have no one who is an expert in everything.
We've got time for just one last question. So do we have any questions for Jordan on student experience or on undergraduate research projects? We'll take from up there.
So Curtin offers a lot of opportunities for projects. So in particular, you have summer scholarships, which they pay you and you come and do projects with your professors. And it's a lot about learning. So you learn a lot during the things. A lot of the time is spent, reading papers and learning the basics for everything that's done. And also allows you, I think most people that take a physics as an undergraduate are kind of thinking towards an academic career, or a large majority are anyway. And it gives you a good insight into, what that might be. Because you see all these great presentations, all these great animations and stuff, but it's not always like that on a day-to-day basis. And it kind of gets you into that mindset of, how to go through plod day to day, and then the exciting bits you get when you get, good results and things, and when your code actually works sometimes, which is always exciting. But yeah, it's always a good opportunity to have that little bit of experience.
And with that, we've reached the end of the Curiosity Showcase for today. So can we thank all of our panelists here? So this I think has been a great event in celebrating curiosity-based research as well as just research in general. And I hope next semester and in semesters to come we can do events, run events like this again, potentially within different disciplines and across disciplines. And so thank you everyone who's here today for being here, and everyone who watches this in the future when it's up on YouTube. Thank you for watching.